All right. So hi everyone. Today's today's 19th of May, and today we'll be starting with Python lecture 4. I always procrastinate, tried not to do so, but let's just start without wasting any time. Where's my VS Code? Okay, let me just open my VS Code. Um, is it over there? Oh yeah. Let me just. Okay. Please ignore the stuff. I was just doing some I was doing some physics, so just ignore this up. Let's just get started with. Let me close this. Okay. Let's start with the lecture 4. Oh, that's a long ass lecture, honestly speaking. Uh, yep, that looks perfect. Let me just increase the volume. Uh, that's perfect.
Okay, so let's get started. Today,
Yeah, let's get started. So, today we are gonna study about loops over strings. Okay, and guess and check binary. I don't know what that is, but let's see. Let me see if I'm recording. Yeah, I'm recording pretty good. Let me just hide my OBS so that I don't accidentally stop my recording.
we will be continuing talking a little bit about loops and seeing some other couple of nuances of loops. And then we'll
So, what do you mean by nuances? So, let me mean. Okay, so a very small difference in meaning, feeling, sound, etc. Okay.
we'll get started on our first algorithm, the guess and check algorithm. And then towards
Okay.
the end, we're going to start talking about binary numbers in advance of seeing our next algorithm.
Okay.
So let's do a quick recap of what we learned last time, and then we'll do a little coding example, and then we'll move on. So we saw last lecture some looping mechanisms, right? We saw while loops and for loops. They're both a way for us to control what happens in the code, and specifically, they're a way for us to repeat certain lines in the code sort of automatically, so to speak. So with while loops, the lines of code were repeated as long as some condition held. And with for loops, the lines of code were repeated for some sequence of values. Okay? And the sequence of values was something that we decided. It was numerical. That's what we saw last lecture. Today we're going to see that the sequence of values can actually be non-numerical as well. So both of those loop types, I guess, had ended at certain times, right? So the while loop ended when the condition became false, and the for loop ended when we've exhausted our sequence of values.
Exactly.
But oftentimes we want to write programs where we break out of the loop prematurely. We don't want the while loop condition to become false, and we don't want to exhaust our entire set of values in a for loop. So in order to exit a loop before the natural end comes, we can use this thing called a break statement. And the break statement allows us to exit the loop, and the loop it exits is going to be the one that immediately surrounds the break statement. So here's a little example of two nested while loops, so one while loop and then one nested one inside it. The outer one is going to run whenever condition 1 holds, and the inner one runs whenever condition 2 holds.
Okay. So let's just try. Let's just try. That's the fourth lecture. So, let's say x equals 1. While x is greater than equal to 10. Uh, you know, print x, and x equals 1 x. So this basically means x equals x plus 1, and then it's going to come out of the loop. So in this case, I'm going to print till 10, from 1 to 10. um it's not running for some reason. Print x. Wait, what? Let me just restart my VS Code. Okay. Are you okay, OBS? Is everything look? Yeah, everything looks perfect. I'm gonna hide this up. Uh, Print. What's wrong? I don't see any output for some reason. Run code. So x equals 1 while x is less than equal to 10. I'm gonna print x, and then x becomes x plus 1. So it prints to 10. Now here's the thing, if I introduce a break statement, it's just gonna print 1. Yeah, yeah. So this is what happening over here. Let me just explain this code to myself. Here's what happening. So initially the value of x is 1. You get inside the loop while x is less than equals 10. Our condition is satisfied, so it prints x. So it prints x equals 1, and then what it does is that it adds 1 to x. So x becomes 2, but this is not a statement that we are getting, so this is something which is Python doing in the background, and then we break the statement. So we come out of the loop, and we just exited the loop. So what we are ending up is with x equals 1 as our output. That's it. So that's the function of break statement.
Okay.
So it skips the remaining expression in the code block, exits only innermost loop. Okay. Okay, so here's one more thing. uh if I introduce another variables, let's say a equals 1 while a is greater than equal to 10, print a, and then a equals a plus 1, and then break. So what's going to happen over here is, as far as my intuition tells, we are gonna print, so initially we are gonna print 1, that would be from x, and then we are gonna get inside this loop, and then we are gonna print 1 again, because a equals 1, the 1 value is basically assigned or bounded to the variable a, and then just because we have a break statement over here, we're gonna come out of the loop. So it's basically gonna exit me out of this particular loop, and we are gonna end up in this loop. So the output would be 1 1, and then 2 3 4 5 till 10. So let's just run and test whether if it works or not. So let me just save this up. Let me run this again. Something's wrong over here. I guess that should be less than equals 10. Yeah. Let me just clear this up. I think I'm wrong with my intuition. Okay. Okay, all right. All right. So I was wrong. I was wrong. I was wrong with my intuition, you know. I was basically wrong with my intuition. So here's what this particular code piece of the this particular block of code is doing. So my x equals 1, I get inside the loop. My condition is satisfied that my x is less than 1. My condition is satisfied. Print x. So our output, let's just write our output. So it's 1, and then the value of for the x increases, so x becomes 2. And then we have a or a equals 1. So while a is less than equals to print, so again we'll get a 1. And then we're going to break out of this particular loop into this loop. Now the value for x is 2, which is again true. So we're going to print 2. And then we're going to get inside this particular loop. But because we came out, let me check the output once more. Yeah, so here's the thing. Because we came out of this loop, this this a has been overwritten by this. So what happened previously, the value of a became 2, but when we got exited because of the break statement, this specific line overwrite a equals 2 to a equals 1. That's one of the reason while we enter this particular loop, our value for a is 1 instead of 2. So it prints 1 again, and then it comes out of the loop, and then it prints 3, and then again 1, and then again 4, and uh, and then again 1, and again 5, and it does until I reach 10, and then again it prints 1. So it's 10, and our x should be less than equals. Now after that, the value for x actually becomes 11. So we do not enter this, our while condition does not get satisfied. So our code just stops, and that's what we get over here. That's the output that we get. Oops.
Now, expression A will evaluate when both conditions.
So let me just do a comment. Day 4 of learning Python. Yep, that looks perfect.
Condition 1 and condition 2 hold, right? So we enter the first while loop and we enter the second while loop. Both of those conditions have to be true. But Python, as soon as it sees this break statement, Python will immediately exit the loop that surrounds that break statement. So the loop that surrounds the break statement is the one that has condition 2, right?
Exactly.
The condition 1 loop will keep going. So as soon as Python sees this break statement, it's going to immediately stop running the while loop. It's not even going to go back up and check the condition 2, which means that expression B will actually never get evaluated. So this is terrible code. We don't want to write code like this because expression B will never be run, right? But this is just to show you the impact that a break statement would have. And expression C will then be evaluated whenever condition 1 is true. Now, condition 2 may or may not have been true along the way, but expression C will evaluate only when condition 1 is true, right? Condition 2 would have stopped being true, and then we're going at the same indentation level as this inner while loop.
So
yeah.
It only evaluates the one time, like it only gives A ones, and then because the break is there.
Exactly, yeah, that's a great point. So it only evaluates this expression A one time, because right after it evaluates it, it sees the break, and then we immediately exit the while loop and we're done. That is a great observation, yeah. And that's
So my sum equals 0 for I in range, so it starts with 5 and gets till 10. Okay, so let's just predict the output using just pen and paper. So you're starting from 5 till 10, and your step function is 2, so you get 5. Then you skip 6, then you get 7, 8, 9. Then you're supposed to get 10, but you're getting 11. Okay, so this is what you'll get. This is 5, 7, 9 is what you get. My sum equals my sum plus I. So okay, so my sum was initially 0, so my sum equals my sum that was 0. So 0 plus whatever the value of I is. So this is basically the value for I. Okay, if my sum equals 5, then break. So it's gonna break out of this particular this particular statement, and for then the value for I will evaluate 7. So we are done with 5. Now the my sum will get the previous value, that was 5 plus 7. What is 5 plus 7? That equals 12. And now the value for this particular condition will not get satisfied. Okay, so it's gonna run once more. So 7 is done, so my sum becomes 12. 12 plus 9, what's 12 plus 9? That equals 21. So again, this condition will not get satisfied, and the output would be 21, if I'm not wrong. It gets break. So this condition is not getting satisfied in the case where I is 7 and 9. In that case, this particular statement will not get satisfied. Yeah, so what happens in this program? I from my intuition, the output should be 21. Let's see.
That's what this code will basically show. So here it is, us doing the break statement, sort of in the same structure as on the previous slide. And what we're going to do is actually just run the Python tutor for this code, just to give you some more practice running the Python tutor. So this is the same code as on the previous slide. I've got a for loop that goes through a sequence of values. Can anyone tell me what are the sequence of values this for loop will loop over?
Yeah, so it's 5, 7, and 9.
5, 7, 9.
That's it. Stop.
And we stop, right?
Stop.
Because 11 is end, but we go up to
There
but
we
not
go.
including n minus 1. So 5, 7, 9 are the only three
Exactly. That's what I said.
values we would potentially loop over. So hit next, we initialize my sum to 0. So in our minds, we kind of think about the fact that we're going to loop through, make this loop variable be 5, 7, 9. So the first time through the loop, I will be 5. We're going to add I, which is currently 5, to my sum. So 5 plus 0 makes my sum 5. And then we immediately see the break, right? Because if my sum equals 5 is true, so we go inside and we immediately see the break statement. This line will never get executed, so we're never going to increment my sum by 1. So the break immediately breaks out of our loop. Now the if statement is not a loop, right? It's a conditional. So the loop we break out of is the for loop. And then there's no other loop surrounding it, so then the program is basically done and we print 5. Okay.
Oh,
Again,
is that so?
bad code. We would never write code like this, but
Okay, all right.
this is just to show
Wait.
you
What's
of is
happening
the
over
for
here?
loop. And then there's no other loop surrounding it, so then the program is basically done and we print 5.
So here's the thing. This particular after the break statement, this particular the loop, the code, the piece of code, or the block of code which is responsible for the loop will not run, and it would eventually print my sum, the initial, whatever the initial value was. In our case it's 5. Okay, so that's an interesting thing to learn. Oh, all right.
Okay.
Okay.
Again, bad code. We would never write code like this, but this is just to show you exactly what happens.
Wait, my doubt is that why it's not returning to. Let me just clear up my doubt. So in this code, my doubt is why after the break stat statement, it's not going back to the loop and exiting the loop. It should exit only the if statement which is inside the critical conceptual horizon and understanding the control flow. This is absolute rule and by the breakstone only cares about the loops. Okay, okay, so it says it says that the break statement, so it only cares about the loop. It does not care whether there if it's inside a if statement or a else statement. Okay, so according to Gemini, it ignores the if statement. When the Python hits a break, it doesn't just exit. Okay, so I totally get it. Okay, okay. So what it means is if there would be another, instead of if statement, if there would be another loop, in that case, our output would be 21, instead of 5. So that's a wrong code. My logic was incorrect. All right.
Happens with a break statement. Right, so there's the code block for the for loop, and this is the code block for the if statement, and the break breaks out of our loop, right, which is the lighter purple, not the if statement.
All right. Okay. You tried write a code for a loop that loops for a for loop over some range and prints how many numbers are in that range. Try it. Wait, what do you mean by that? Write a code that loops a for loop over some range, okay, and prints how many even, okay, so how many even numbers are in that range. Okay, so how many even numbers are in that range? That's an interesting question. Okay, so let's say you have a variable. How do you check whether a number is even or odd? So as far as I remember, if there is a number x, so not a number, a variable x, and if its modulus gives me 0, in that case it's a even. So it's an even number. And if else, else else it's an odd number. So how we are supposed to uh code code for it, um okay, let's just let's just try to start with control A. Okay, okay, so we have a variable, let's say x that equals integer, and it's going to be our input. Enter some range of number. Okay, for I in range, uh so I'm gonna start with, let's say we are getting started with just 1. and the step function is 1. Check if check if you know, if x modulus equals 0. If that's true, if that's true, print is even, and then we don't have to write I equals I plus 1 because this for function eventually does that work for me. I have a doubt why this thing is giving me an error. I don't know why. Okay, so modulus 2. Okay, my bad. So x modulus 2, that should be equals 0. So in that case, it's a even. So let's say, let's just try this code on the paper before running it. So let's say x, let's say for sake x is 4. So um it's gonna start with 1. It's gonna check if, my bad, I think I'm doing something really wrong over here. I think we should have I over here. We should have I over here. So I, so 1 modulus 2 is not equal to 0. So this condition is not get satisfied, and it's gonna jump over this loop again. And now the value for I is actually 2, and it's gonna print till, so the value for I would be 1, 2, 3, and 4, and it's just gonna stop over here. Because my input was 4 and I added 1, so it should be till 5, but because the stop function, its real value is actually the stop function, the value of stop function itself minus 1. Okay, so it's not going to print anything. So now the value for I is 2, so 2 modulus 2 is 0. Okay, so in that case, this particular condition should satisfy, and I should get a output as I, which is 2 is even. 2 is even. Um, but this is not the question. The question is how many even numbers are in that range. How many even numbers are in that range? Okay. Okay, so in order to count, I guess we should introduce another loop. So let's say we have another variable a equals 1, and for a in range, we are starting over 1. Wait, I think I should not write this. So we are starting over 1, and we are going till what? Wait, let me think. How we are supposed to do counting? Mm, let me think. Let me think. Let me think. How we are supposed to do counting in this case? Um, then we have to store a number. Wait, let me think. I'm not able to figure out. For a in range, so we are starting over 1, and we are going till let's say uh, y. So we have initial value for y equals 1, for y plus 1, a equals a plus 1. No, no, not this. I don't know what I'm doing. Wait, let me think. Let me just think. This one's actually confusing. Okay, wait. I'm just gonna remove this code and I'm just gonna run. So 2, 4, 8, 10 is a even number, so our code is working. Now, what I'm actually supposed to do right now is count. So how do I count? How do I count this shit? I need to count this shit. So for I in range, let me think. Mm, let me think. Let me think. So for let me just put that code again over here. So we have initial value for y equals 1, and then we have introduced another variable, print a equals. No, we don't have to do that. We actually have to do y equals y plus 1. Okay. Um, and then I think we need to break it, print y. So it's going to come out of this particular. So if okay, break. So it's going to come out of this particular, and I'm going to get the value for y. Let's just try to run it. Input 10. Okay. So 2 is a even 2 y. I think I should not break this up. Okay, let's not just break this print y. And so I'm actually getting the value for y equals 3, which is incorrect because what I need is 5. So what's happening over here? Let's see. So we are starting from a. We are starting from a, and we are going till y plus 1. We should go till y. Okay. No, I think it should be y plus 1. Then our y becomes 2, and then it exits the loop. Um, okay, 10, uh, a is not defined. Okay, let's just see the code.
Okay, so let's have you write a little bit of code, and this is sort of maybe a little.
So this particular part, this particular part, which is into some range, so let's say 15. So this is correct. I'm actually confused. How am I supposed to count those numbers? I is a even. And then I think we introduce another variable, a, which has initial value equals 1. And when you come out of the loop, when you come out of the loop, you don't break, wait. When you come out of the loop, you put a equals a plus 1, and then you print a. Print a. So what it's going to do is it takes the value for a equals 1, and then it exits the loop, so the value for I becomes 2, and a equals a plus 1. So a should be 0. I think this won't even work. Let's put 10. A is not defined. So a is 0 initially. Let's try to put 10. We get 1. We get out of the loop. So I think we need to define this somewhere else. I think we need to define a equals 0 over here, and it says a equals a plus 1, and then it gets out of the loop. So now the value for a becomes 2. So okay, this should work. It worked. Okay, it worked. So what I'm gonna do, so the total number of even numbers in this range are a. Okay, this should work. So we know in the natural numbers from 1 to 100, there are 50 even numbers and 50 odd numbers. So I'm just going to put input as 100, so that okay, so we get the total number of even numbers. So the total number of even numbers in this range is 50, and that's how I cracked this code. Okay, it was tough, but I did it somehow.
Practice with just loops in general that we saw last lecture. There's no
So
break
this was a good question. This was a really good question.
really in this
I would say, it actually opened my mind.
particular program here, just a little bit of practice. So what I want you to do is to write code that basically has a for loop running through this range. So for I in, pick one of these.
Let me see if I'm recording or not. Yep, looks everything perfect.
I want you to write code within that for loop that counts how many even numbers are in that range.
So the original question was this, so this was the original question. So if I print, let's say if I give a number till 10, so the output says the total number of even numbers in this range are 50, which is pretty not 50, it's 5. And if I print till 15, so how many numbers should be 7? Okay, are 7. So this is what our actually code, this is how our actually code should look like.
Right, so including the 0. So for range 5, your counter should basically pick up on the fact that 0 is even, 2 is
Okay,
even.
so it should start with a 0. In that case, if I take a range till 10, so what it does is, so 0, 2, 4, 6, 8, and then 10. So 1, 2, 3, 4, 5, and 6. And that's how we get our output as 6. Okay. Okay, all right.
Even, and 4 is even, and then that's it. So it should print 3. So here is the you try it inside
Okay,
the
so
Python.
I did another mistake. So if the range is 5, then it should, if the range is 5, according to the lecturer, she's actually saying that, let's say, I my range, let's say my range is 5, so the program will run like this: 0, 1, 2, 3, 4, and it does not take 5, and even numbers are 0, 2, 3, so the output should be 3 in this case. So for that, we just have to remove +1, and again gonna run till 10, and in that case 5. Let's check this out. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's not gonna, the value for I will not be 10. Let's see how many even numbers are there. So there are 1, 2, 3, 4, and then 5. So what's the output that we got in the last run? So that's 5. So this is how we are supposed to make program. Okay, I get it.
File for today.
I get it. I get it.
And I've already started you off with this for I in range 5 as the first one. And I'll give you a couple minutes to just write the code in here. Okay, would anyone like to start us off with some code? Or give me, yeah. Yep. So this line of code is going to take our I, right? So in fact, what we could do to remind ourselves what I is, and this is very helpful for quizzes as well, we can write a little comment here that says I is 0, 1, 2, 3, 4, just so we don't have to remember this fact. We can just always look here and know what I is going to be. And then this line of code, absolutely correct, is going to take I and grab the remainder when I is divided by 2. Okay? And if the remainder is 0, that means that the number is even. And then what do we do inside here?
So for odd, we could have just used this, this operator, not equals. I guess that's correct. Not equals operator. Not not equal, OPR operator. Okay, yeah. So that's the not equals operator if we have to check for any odd number or the total number of odd numbers in our range.
So when this is true, when it's even, how do we keep track of whether, or how many
I don't
times
know why I feel kind of exhausted today, but anyways, I think I've not taken my sleep properly.
this condition occurs? Yeah. Yeah. Yes, exactly. Should we create a variable? Yes, we can. So let's call it even nums. And we'll probably want to increment it by 1, right? Because here's another number that's even. So even nums plus equals 1. And then let's remember to
Initialize it.
initialize it right before our loop, right? So initially, before we even start our loop, we have 0 even numbers. And then each time through our loop, we see one that's perfectly divisible by 2. We're going to increment this little counter by 1. Okay? And, oh yeah, not the same variable, thank you. Even nums, yeah. And the mental model you should have sort of at this point or be getting is just the fact that these 3 lines solve our problem.
Exactly.
It does the automatic counting for us.
Exactly.
Right? Because I will take on 0, then 1, then 2, then 3, and then 4 automatically as the loop goes through this sequence of values. And so at the end of the loop, so sort of at the same indentation level as the for loop, all we need to do is print how many of these numbers we have.
Even underscore num.
So if we run it, it'll print 3. And if we change this to 10, it'll print probably 6, right? Because it counts the 0. Right? Questions about, yeah, please.
Is there anything I should look out for if mine prints out 2 instead of 3?
So if you're undercounting, you maybe did you initialize even nums to something else? Or maybe this is not incrementing right, or maybe the range is different?
I'll try the range of times.
Yeah. It worked? Awesome. Okay. So
Strings and loops. So code to check for letter I or U in a string. Okay. So now we are using indexing, the length function, and the slicing function, we are using multiple things at the same time. Crazy.
iterating through,
Iterating through,
using
okay.
for loops to iterate through sequence of values is pretty useful. Let's
So,
take another look here at this.
so I'll just try to understand this particular code before the lecturer explains it. So it says that we have a string over here which says something. I don't know what it says. Okay. For index in range, the length. So we have a variable index. It's going to start with a 0, which is this D, and it's going to print till length. So length. Okay, length -1. So okay, let me just revise one more thing. Um, let me just revise one thing. So let's say NIKHIL. So it's 0, 1, 2, 3, 4, 5. That's the index, if I'm not wrong. And 1, 2, 3, 4, 5, 6. That's the len. Okay, let's say if A equals this, so that's len of A. Okay. Okay, so it's gonna start from the 0 till 5, which is perfectly okay. If S of index, okay, all right, equals I or S, okay, so you're using a I or, okay, print, there's a I or U, okay. For Karen S, if character, so we have another code for Karen S. If character equals I or print there's I on U, okay, so that's an alternative code for this. Here we are not particularly introducing a new variable, which is a good thing. And I think that this last code is even more efficient as compared to the first one and the second one.
Particular
So for Karen S, for character NS, if char is in IU, there is a I or a U. Okay, that's interesting. There, why is it treated as a single variable or two different variables? I don't know. Or is it a mistake?
program. So this program is this set of code, this code, and this code actually end up doing the same thing. But let's look at the top one for now. So this is a program that takes in a string s as sort of an input, so to speak. It iterates through the numbers 0 to the length of s, right? So for index in range len s is basically going to say for index in range 13 or however many letters this string has, right? D-E-M-O space L-O, like all those letters, there's probably 13 of them or something like that.
Whatever.
So this line of code here is going to have our index take on the values 0 through 13, representing the index in S, right? So the lowercase d will be at index 0, the lowercase e will be at index 1, and so on. So with this index in hand, the next bit of code, if s square bracket index equal I, will check for me if this particular character is an I, or that particular character is a
Is
U.
U.
And every time that happens, I'm going to have this print out to the screen. There's an I or U. So inside my code here, this is the first one, and I run it, it's going to print out that sentence twice because there's only 2 I's or U's in here, and if it repeats, it'll print it out twice. So there's 1 U and 1 I. Okay. But this code can actually be written a lot simpler. Okay? Notice it took me a little bit of a while to explain it, and probably at first glance, it would take you a little bit of time to figure out what it's doing. And that's because we're actually relying on the index as kind of a middleman, right? We're iterating our for loop through the index, and then we're indexing into that index variable to grab the particular letter. It turns out that with for loops, right, I told you can iterate over any sequence of values, not just numbers. And remember that strings are actually just a sequence of characters, right? Case-sensitive characters.
Exactly.
So in Python, we can actually write code like this. So the middle box right here. It has our for loop iterating through each character in the string directly. So no longer are we looking at the index, 0 through 12, but we're looking at the letter directly. So our loop variable, which I called char, but you can call whatever you'd like, is now going to take on values that are the letters themselves, one at a time. So the first time through the loop, char will be lowercase d. The next time through the loop, char will be lowercase e. The next time, char will be lowercase m, and so on. And so now we've got this sequence of values that's the letters directly.
Okay, so here's one more thing that I would like to mention. Our program in this particular example, our program has been designed to check for the lowercase I or lowercase u only, and if s would have contained any uppercase I or u, it would have just not read that. That condition won't be, this particular condition won't be won't get satisfied for any upper letter I or U. So that's a bad code in my perspective. So, or you could have just add or s of index equals uppercase U and for I also. So in that case, it would work for upper letter also.
So when we check if the letter is an I or a U, all I need to do is check if that character, right, char, my variable, is equivalent to I or equivalent to U. And it's going to be the same, and it's exactly the same code. So this is the one we had before, and this is the one I just went through. And again, it prints out that sentence twice, right, because it's the same starting string. So the sequence of values now is our characters directly, right? It's the letters directly. It's not the index itself. And it turns out there's actually a much more Pythonic way to write the code, this middle box down here. So in the bottom box, the only part that I've changed is the if statement. And I'm using this in keyword to test whether the character that I have in hand, lowercase d, lowercase e, lowercase m, and so on, is in this sequence of characters, I or U. And for this case, it's not so important, right? Because in the middle box, we could do if char is equal to I or char is equal to U, which is fine. But if we wanted to test if the character is one of the digits 0 through 9, this if, or would become a really long line, right?
Exactly.
And so all we can do is, if char is in some particular sequence of characters, Python will automatically turn that into that longer if it's this, or if it's this, or if it's this, or if it's this.
Okay, let me just check this for my name. So let's say s equals string, which is going to be our output into. I don't particularly have to write string because um, for what was the code for character in S character in as if care in it what what okay. So I have no idea how it works. Let me just ask Gemini. How does this work? I mean, if I have just written IU, what the Python and how the Python detects it as two different words ins instead of a single word IU. What's happening over here? So what's happening over here? That's a fantastic observation. You're hitting on a core concept of the Python substring membership checking. Bro, what's that? Python isn't detecting them as a two different word, instead it's treating you as a single target sequence and checking if okay, alright. If Karen, okay, I get it where it's going. Because for Karen I, it iterates over string, the variable character only check one single character at a time if it type in 6 times. Okay, I get it. So, okay, I totally get the point of using this particular block of code.
This and so on. Okay.
How many views are on this video? 1.3? 1.3? 1.3 lakhs. Okay. So I've completed 3 sessions and I'm currently doing the fourth. Let me see if there are any new comments. Okay.
Okay, so the big idea here with for loops is that, yes, we're iterating through a sequence of values, but we're not limited to just numbers. And that's the cool thing about for loops. You can iterate through characters directly, and we're going to see later on we can iterate through lists of numbers, lists of strings, and a whole bunch of other things. So let's write a slightly more complex program. This was version 0.
Robot cheerleaders. So, uh, okay, so we have a string over here, the word input. I will cheer for you in the robot. Okay, and letter times is equals to enthusiasm level. Okay, I'll be back from washroom. I know. I think I drank too much water. I'll be just back in a minute. All right, I'm back. I'm back. You know, let me just stop the recording and I'll be back after 10 minutes because I can find my. I think there's one thing missing. Okay, so I'm back and I eventually ran into some problem. Let's
0.01.
let's just start. So for C in Word, if C in Word, so C is basically an variable. So we're iterating the word input. Okay, let's just try this code on pen and paper. There it is. And let's see what it's gonna do. So let's say your input word, your word is, let's say it's Nikhil, Nikhil. That's my name. And times. So let's say enthusiasm level is 10 on 10. So for C in the word, so it will go through this word nickel. If C is in a letter, so yeah, there it is. We have I, we have L. You know, let's say it's Nikhil instead of this word. Um, Nikhi. So we have N. Yeah, pretty much. That's 1, 2, if I'm not wrong. We don't have K. Okay, that's all we have got. So we have print F. Give me and C. So it will give me that word. So it would give me N. Initially, I think I would get a N. They're using F strings over here, and I haven't practiced with N strings. So I'm gonna take a guess over here. Else print, give me a C and letter. So it's actually getting satisfied. What is that spell? For I in range times, print. Okay. So now I'm gonna get out of my loop. I'm gonna get out of my loop for scene word. So it searches for I. So it's gonna print I. And it's not gonna print K. Not gonna print. So it's gonna print H, NIH, then I, and then L. And what's that spell? For I in range times, so it starts from I till times, means it will start from 0, 1 till 9, print word, so word. Wait. I'm pretty confused about this one. Okay, let's just try this.
One of the cheerleader robots you see up in the corner there that I wrote. The robots are not mine, but the code is. So here's a little bit of code that kind of
So that was a joke. The robots are not mine, but the code is. Okay.
puts together iterating through strings directly and iterating through numbers directly. So let me show you what this program is actually doing, and then we'll go over the code. Somebody give me some noun you're really excited about. What is that? What? What?
Wait, what?
Never mind.
Wait, what? What?
Something else that I know.
Wait,
What is
what?
it? Pineapples. Okay. Pineapples. Okay, so there it's going to cheer for us about pineapples, and let's say we're enthusiastic level 8 about pineapples. All right, so this is my cheerleader program, so I typed in a word.
Give me a P. Okay. Okay, so Wait. Wait. Let me just get to Gemini. Convert. Give me the code out of this image. Okay, I'm gonna try writing my name and let's see what happens. There it is. I'm gonna get to my VS Code and I'm gonna run this code. Enter a word. So it's nickel. Give me an enthusiasm 10. So let's see. So it gives me a I. It's give me NIKHIL. Wait, do we have K over here? We don't have a K over here. So why does it print a K? Oh, I get it. I get it. So here's the thing. Here's the thing. Even if so here's the thing. If I remove this code, I get the output what I wrote over here. So I'll get NIHIL. I won't get K because according to the code, uh, you know, if even if that character, let's say the K was not present in this specific string, I would still get that particular character as an output because that's what our code is designed to do. So I'm gonna save this up and again I'm gonna run the code 10 on 10. Have a look. NIHIL. NIHIL. Yep. Yep. So okay. I was definitely ignoring this particular piece of code. My bad, it happens. It would definitely take some time for me to learn, and that's totally okay, but okay, I understood. I understood this.
Word, and I typed in an enthusiasm level for pineapples. And then all it does is, and notice the repetition, which computers are really awesome for. Give me a P, give me an I, give me an N, and so on, right? What does that spell? And then it does pineapples with 3 exclamation marks 8 times, because that's how enthusiastic I'm about pineapples. All right, so let's look at the code that actually does this. Notice there's 2 parts to it, right? There's the part that does the spelling, and then there's the part that does repeating the word some number of times. So these are 2 separate loops. The spelling is up here, this for loop here, and then repeating some number of times is down here. Okay, so the part where we do the spelling has a for loop that iterates through the letters in the word directly, right? I'm not doing anything special with these letters, so I can just iterate through the letters directly. So for W in word, where word is the input that I grabbed from the user, W is a loop variable that's going to first be P, then I, then N, then E, then A, and so on, right? And then I have an if-else here, and if you look carefully, the only difference between the if, what we do inside the if and what we do inside the else is whether we type in un and then a letter, or a and then the letter, right? Because some letters make sense to say, give me un a, as opposed to give me a. It just doesn't sound right in English. The letters, where it makes sense to do un, are defined up here. So notice they're just defined as a
Okay.
really long string.
All right.
And so the if statement uses that in keyword we saw on the slide, right? It says if W,
So I totally get the idea of this particular problem.
so if that particular character is one of these, is in this sequence of characters, then print give me un, and that particular character. And otherwise, it's not one of these letters where it makes sense to say un, so then you just print give me a, and then that letter. Here, I just rewrote these two print statements using f strings, which we talked about back in lecture 2, just to show you how you could rewrite it with f strings, but it can be done both ways. Okay, so at the end of this, we've done the spelling, and then we have a print statement that says, what does that spell? And then the last part is to repeat that word some n number of times, whatever the user told us. So I saved that number of times in a variable called times, and then all I do here is I have a nice little for loop that goes through how much that number is, right? So range times means it's going to be 0 all the way up through and including times minus 1. That's a total of 8 times in this particular case that it loops through, and then all we do is print the word with 3 exclamation marks. Notice that this print statement that's inside the bottom for loop is not actually doing anything with our loop variable, right? Our loop variable here is I, but we're not doing anything with it. And that's totally fine, right? Because all we're using in the times in the loop variable in this particular case is to do this action some number of times, right? We don't always have to do something with that loop variable. Any questions about this code?
No.
Yeah.
Could you also have used if statements for the print?
Could you use if statements for the prints? Which prints? These ones?
Yeah.
How so?
I mean, to evaluate like the W's instead of having to concatenate things. I mean F, not if, F.
Oh, F strings. Yeah, we could have done it like this. Yeah, so this is how it is F, and then we do the characters themselves inside the curly brackets. Yeah, oh no, that's okay. It's okay. Yeah, there's a question, yeah.
Can you explain how that last for loop works since we're not actually doing anything with I?
Yeah, so the last for loop is still going to iterate through times, right? And the loop variable, each time through the loop, will be 0, then 1, then 2, then 3. We're not doing anything with the I, right? The stuff that's indented is going to get done, but we're just not using the fact that I is 0 or 1 or 2 at all.
But it'll increment itself.
Yeah, it increments itself automatically. We're just not using it. Yeah, exactly. Okay. And that's what I said. Okay, so let's have you write a little bit of.
Assume you're giving a string of lowercase letters in a variable as count how many unique letters are there. For example, unique letters. So what do you mean by unique letters?
Code. So let's assume you're going to be given a string of lowercase letters, right? So we're not going to bother uppercase, lowercase, just assume you're given lowercase letters. It's stored in a variable s, so as an example, s is equal to ABCA. I would like you to write some code that counts how many unique letters are in this string, right? So notice A occurs twice, but the count that your code should do for this particular in this particular string should just be 3, right? We don't want to double count the A.
Alright, so unique letters. Okay. That's what they meant by saying unique letters. Okay, so how can we do that? That's a really good question, honestly, for someone who has just got started with learning Python. I think I should try that on VS Code. So let's say s equals input enter something, and how we are supposed to do that? Like what's the algorithm behind this? I need to think of an algorithm which would do that, but count how many unique letters are there. So what you do for x and s, if let me just think. I really have no idea how we're going to do that. I really can't think of an algorithm which which can do this stuff.
So there are
I
three
really
unique
do.
letters in ABCA. They are A, B, and C. So I do have a little hint.
So you go through each character in S, keep the track once you're in the variable, add the character from S to C string if they are not already in the character. Mm, I can't really think of a program or a algorithm. Let's just look at the
It
solution.
involves the use of an extra variable, as these programs usually go. Uh, Try to think about having this extra variable be a string that contains everything you've seen so far. So as soon as you see a letter that you haven't seen before, add it to the string variable that marking that you've now seen this letter, and then use this seen variable to write the rest of it. So as you go through your letters, make sure that you're going to check whether you've seen it already before recounting it.
But how can we do that? I can't
So as
I,
usual,
I
it's
can't
in
really think of
here
it.
around line 76. This is the code to do it. So I'll give you a couple minutes and then we can write it together. Okay. So let me just work through it. And this is something that I think is pretty useful in a quiz situation. It's just writing things on paper first, just because it's like programming computer science class doesn't mean we have to start coding right away. So it's really helpful is pretty useful in a quiz situation. It's just writing things on paper first, just because it's like programming computer science class doesn't mean we have to start coding right away. So it's really helpful to just kind of put some ideas down on paper. So the way I would go about this problem is clearly I have to touch each character, right, in the string S. So already for me, I need to have a loop. So as I'm looking at each character, I'm going to keep track of it. So if it's not something I haven't seen, so if it's something I haven't seen before, what I want to do is say, okay, I have now seen this A. So I'm going to add it to a seen variable. And then I'm going to increment a counter, right? I've seen it once. So
Okay, all right. So, oh, all right. And then what we are going to do, sane variable is equals to sane plus, sane plus x. If, okay, so here's the thing. Here's what we are actually gonna do. So let's say our word is A, B, C, D, and then A. So what we're going to do, we're going to take A and store it in some variable, let's say X, so it gets stored. And we are somehow going to create a loop which is going to check for this our string again. It's going to store B, and then it's going to store D, and it's going to store A, B, C, D. Okay, but along with that, we're actually going to add a if statement, MENT, if statement to check whether the word or the specific character that we are checking is already in the X or not. If it's in the X, we are going to break. And once we break, this A will not get stored in this particular new string, which is X. And that's how we get the solution for this particular problem. So sane plus x. So we need to define sane. So what we could just do is sane equals null. You know, that's a null string if if x. So if x in scene, then what we are going to do is break and print scene. So enter something, Nikhil. Okay, my bad. I think I did some mistake. So let's see what's happening over here. So for x in scene, so x starts with let's just copy and paste this code over here. So what's happening over here, um my input is, let's say, Nikhil. Scene is basically a empty string for x in s, so it starts with n. Scene equals this empty string plus x, which is n, and then it checks if, oh, my bad, okay. So the mistake I did over here is this break statement is basically pushing me out of this for loop. So that's the mistake I did, I guess. Yeah, that's the mistake I did. So I think I need another loop over here. I need another loop over here for y in scene. Check if and then break. I think this should work, but we are still going to check this. We are still going to verify this code. Okay, so let's see what's happening over here. So my input was, let's say, Nikhil. It's initially an empty string for x in s. So this x initially has value as n, and then scene. So let's just call it s, becomes this empty string plus n. And for y in scene, so y should be n, this n. Actually, it should not be n, it should be that empty string plus n. We are just adding two strings, an empty string and n. So that's going to create a blank space before n. If x in scene, wait, um, so what was x? Yeah, so if x is in the scene, we are going to break. But this condition does not get satisfied. Let's say let's just take a simple example. Let me just take a very simple example. Okay, let's say I took a. Okay, so initially the x is going to be a. So scene is equal to, so our s becomes a. For y in scene, so y is basically a. If x in scene, if x in the scene, okay, so it is, so it's gonna break. Okay, x in the scene, yeah, it is. I think we have to introduce another variable over here. Let me think. Let me think. Mm, Let me just think of it. If our x is in the scene, No. Y in scene, I guess it should be. It should be Y in scene. So let's say we have Y over here. No, it's still gonna break. Okay, let's say it break for X in S. So now the X has value B. Scene is equals scene plus X. So scene would be AB, and now it's gonna check if Y is in the scene. So what was scene? Scene, it was initially here the value. Um, I'm getting really confused. Too many variables. I'm getting confused. I'm just gonna watch the lecture.
Count maybe equals 1 now. The next time I look at the next letter, I'm going to say it's a B. Have I seen it before? No. Let me add it to my scene variable
Okay,
and increment my count.
2.
Next time I'm going to look at the letter C. Have I seen it before?
No.
No. I'm going to add it to my scene, and then I'm going to increment my count. And then the last time I'm going to look at this letter A, I'm going to say, is it already in my scene?
Okay. For X in scene, not in the scene, for an S, what I'm gonna do is scene is equals to scene plus X. So scene is basically it starts with A. Okay, that's what I can do.
Yep. So I'm not going to do anything with this one, right? So when I see a letter that's already seen, that I've already added to my scene variable, I basically do nothing in my code, right? So the most of the work happens when I encounter something I have never seen before. So does anyone have some starter code or something we can write? We don't have to write it perfectly top to bottom. We can write pieces here and there.
So after like you define your things up there,
Yep.
I wrote for car and S. And I think this is not supposed to write it, but I said like if car and S in scene equals.
For curriness, okay, so that's what I did. Initially, this for characteriness. So we are starting with A. If char is in the scene.
False, but like I want to say if it's not in.
Okay, so if it's in scene, then we are gonna add character to the scene.
Yeah, so that's a great start. So if you want to say if it's not in scene, we can just say if char or car, however you pronounce it, is not in scene. So that takes the inverse of true or false, whatever this is, right? Because in scene will either be true or false, and not that will be false or true, right? So that's perfect. Yeah.
Can you quickly, when do we use the word not? When do we use like the estimation code?
Oh yeah, so we can use not when we're dealing with booleans, right? So something, an expression that evaluates to true or false. That's when we use not. And the not equal, so the exclamation mark equal, is used when, with other expressions when we're testing for equality.
Equality.
Right,
Yeah.
like 3 not equal 2, or like A not equal B, or something like that, right? So things that could be numerical, not necessarily just true and false. Yeah. Okay. So if char is not in scene, so if I haven't seen it before, what do I want to do? Yeah. Yep. Yep. So we can append the character that we just looked at to our scene list, right? Just as we had done
Exactly.
incrementally here. So that takes care of adding the character one by one if we haven't
Okay, that's what they have done.
seen it to our scene. Good. Anything else we want to do?
We don't have to, specifically for char we don't specifically have to use the break statement. So for character in S, where's the code? If char is not in scene, then what we're going to do is scene equals scene plus that character, not in scene. Okay, and then we are going to print scene something A B C D.
Incrementally here. So that takes care
Okay, it's correct. A B B C D A B C D.
of adding the
Okay.
character one by one if we haven't seen it to our scene. Good. Anything else we want to do? Or we can even test it out like this, right? So we can print scene each
Scene.
time through our loop. Right? So
AB,
first it's A, then it's
ABC.
AB, then it's ABC, and then the last time it should still be ABC, and it is. Okay. And the last step is to just do what the problem asks us to do, which is to print how many characters are, or how many unique characters are in this list, or in this string.
So for that we could just introduce, a variable. So let's say x. I've not used x, so x equals 0, and what we can do is x equals x plus 1, and then we can just print total q unique words in this is just x, so that should work. So 1 2 3 4 and then 5. Yeah, that's correct. But here's the thing, if I take n, I, and I capital, KHIL, then it should be 6. Exactly, because the capital letter I and the lowercase I is not same, so it treats this program treats this as two separate unique characters, so that's why it prints 6.
Yep. Yep, we can have a counter that is initially 0 before the loop, and every time we add a new thing to our scene
Exactly.
string, we can increment our counter, and then that takes care of the bulk of the work,
Print.
right? This does all the counting, all the adding to the unique scene, and so at the end of the loop, we have this number in hand, and then we can just print it. So with this particular case, it's 3. If we add more A's in random spots, it's
That-
still going to be 3.
Won't
Right.
change the output.
Yeah.
Now to the
Yeah, so now that we have... Yeah.
now to the
Why the audience is inaudible all the time?
Yeah, so now that we have some code that basically that works really well, we can make improvements to it. So one improvement that's suggested is instead of keeping a counter variable, we can actually just recognize the fact that the length of our scene is just all the unique characters we've seen already, right? Because when
Exactly.
we double up on something, we don't...
Exactly. So instead of writing this, so we could have just print the len of scene. That's it. So A, B, C, D, A. That's 4, correct?
don't re-add it. So all we can do to print out...
So I'm just going to write that in my notes, that instead of instead of using a counter variable, we could just use the length function.
The number of unique characters is to just say I'm going to print out the length of scene. Okay, and now there's no need to increment any sort of counter. And so that still gives us 3. Questions about this code? Does it make sense? Okay. Notice there's no else, right? We just have a nice little if. There's no else because there's nothing to do when we've already seen the character. So we could have else pass. And pass is just it's just a keyword in Python. You see it's turned blue because it's a keyword in Python. It just means do nothing. Right?
Oh,
So
okay. So all
we wouldn't
right.
write this, obviously, but that's if we had an else case, that's what we would do. We just do nothing. Okay. Other questions about the code? Is that right? Sorry, say again? Why are we printing the length of scene here? So we're printing the length of scene because we see that whenever we add a unique character to this scene variable, it's one that we haven't actually seen before, right? And so the only things I'm adding to my scene are things that are new. And so even as I was going through manually here, I said, I've seen the A, I've seen the B, I've seen the C, I added them one by one. And then when I saw the duplicate A, I didn't add it to my here, right? And so basically, this scene already contains all the unique characters in my list, in my string, original string. Yeah. Okay, so quick summary of what we've seen so far before we start looking at our first algorithm. So we've seen objects, right? That's how we write Python programs. We manipulate objects by saving them to variables so the values are more easily accessible. We have expressions that evaluate to different things, integers, floats, booleans, things like that. We added branching as a way to control, as a control flow mechanism to our program, right? It says, hey Python, either evaluate this set of statements or this other set of statements depending on whether this condition is true. And then we added the last mechanism for control flow, the looping mechanism, that said, either loop or repeat this code while some condition is true, or loop this code for this sequence of values, okay? So really with that in hand, we basically have a really nice toolbox of things that we can use to write interesting programs. That's kind of all we need. But this is not the end of the class. We're going to look at other things that will make our code neater, more readable. We can write more of it more efficiently and things like that. But really, if you want to just start writing little algorithms, this is all we need in terms of Python syntax. So the first thing we're going to apply this knowledge to is our very first algorithm, called the guess and check algorithm. So
All right, so process and exhaustive enumeration. What does that mean? So I've heard this term exhaustive in probability while I was doing MIT 6.041. Applies to a problem where you're able to guess a value for solution. You're able to check if the solution is correct. You can keep guessing until find the solution or have guessed all the values. Okay.
another word for the guess and check algorithm is exhaustive enumeration. Okay. So the idea here is
Enumeration.
that we're given a problem,
Okay.
We can guess a value for a solution.
Okay.
Okay? We'll just do a guess, and then we'll test whether this guess is correct. Does it solve our problem?
Okay.
If it does, we're done. We found a solution to our problem. If it doesn't solve our problem, we're just going to keep making guesses until we've exhausted our set of possible guesses, right? So either we find the solution or we say we weren't able to find a solution to this problem. Doesn't mean that one doesn't exist. It just means that with guess and check and exhaustively enumerating all these possible values, we were not able to find a solution. So in terms of a flow chart, the way this looks is we have an initial guess. We ask, is this guess correct? If it is, we're done. And if it's not, we're going to choose a next guess. So let's look at finding the root of a perfect square. And that's our problem. And we're going to say either we found the root of this perfect square, or we say this is not a perfect square. So with guess and check, we can say, well, what if we want to find...
So now we are introducing some mathematics over here. It's going to be fun.
What if we want to find whether 7 is a perfect square? If it is, what is its root? And if it's not, say that it's not a perfect square.
Okay, so like here's what we can do. Square root. Okay. So if we take, mathematically, if we take the square root of 7, it would be a float value. And if it's a float value, we can say that it's not a perfect square, And let's say if we took 9 and if we took the square root of 9 or square root over 9, we would eventually get 3, which is an integer. In that case, we can use conditional statement to tell whether 9 is a perfect square or not. So in that case, 9, since the square root over 9 is 3, which is an integer, 9 is a perfect square. I think that's what they're trying to say. Let's
Well,
see.
we can make an initial guess, 6. That's not the right solution. We can make another guess, 9. That's not the right solution. We can make another guess, 2. That's not the right solution. We can make a guess, 0. That's obviously not the right solution. We can keep guessing randomly like this, but it's not going to be very efficient, right? What we want to do is use the power of computers, and computers work with these sort of patterns in hand, right? Remember range starting from 0, following a pattern, going up to some number. So the idea is to be systematic, and then we can really harness the power of programming and computers being able to do things really, really quickly for us. So for that same problem, finding out whether a number x is a perfect square, let's be systematic and start with a guess of 0. Two cases. The number we're trying to find the square root of is a perfect square. Let's say 4. We're going to start with a guess of 0. Is 0 squared solve our problem? No. Increment. Does 1 squared solve our problem? No. Increment. Does 2 squared solve our problem? Yes.
Okay.
We are done.
All right. So here's what we are doing. But I don't think that this program is very efficient for a very large number, So this is what they are doing. Let's say we have given a number x, let's say, and a variable x. We are starting over 0. We are checking where 0 square is x or not. If it is, let's say x, our given variable, input variable is 16, then what we are doing, if it's not, then we are incrementing 0 by 1. So we check whether 1 square equals x or not. So in this case, it's not, till, let's say, we get 3. So what we get is 3 squared, that 9, which is not equal to x. So our condition is not satisfied yet. But if we get to 4, so 4 square is 16, that equals x. So in this case, our statement is, satisfied. So we can say that 16 is a perfect square. But what if our input variable is a very large number, like let's say maybe a 10-digit number or what? It's probably not efficient if I'm not wrong. Let's see if there's something else to this algorithm.
What if x is not a perfect square?
Okay. So what if x is not a perfect square? In that case, we might add a conditional statement which would check if our our variable, not the variable but the loop. So let's say our x is not a perfect square, and we started over x 0 square, so that's not equals x. 1 square not equals x. And let's say we reached a number which is equals to x. So if this particular number is equal to the input, or the number for which we want to check whether if it's a perfect square or not, then that conditional statement will break the loop. I'm just assuming. So it will break the loop, and hence we'll get an output that the input is not a perfect square.
Okay, let's say 10.
10.
Let's use the
So
same.
so by taking x equals 10, what we are going to do is 0 square is not equals 10, 1 square not equals 10, 2 square not equals 10. Okay, 3 square is not equals 10, but simultaneously it's going to check if 0 is less than 10 or not, if 1 is less than 10 or not, if 2 is less than 10 or not, if 3 is less than, not 3, but actually 3 square, my bad. So 0 square is just 0. So whether 3 square is less than equals, let's say, 10 or not. But if we check for this condition, if 4 square is less than equals to 10, in that case it would be a false statement. So it's a false statement. In that case, our conditional loop is going to break, and we are going to stop, and hence our output would be that the given input in our case, which is 10, is not a perfect square.
Systematic approach of guess and
So
check.
so use algebra if the guess square is big. That's what I just said, bro, that's what I just said. If the guess square, if the guess number, which is incrementing by with starting with 0 and incrementing by 1, is bigger than x, is bigger, so 4 square, which is 16, is bigger than x, then we can stop. Then stop.
We're going to need to add a little bit of algebra though, because if we
Exactly.
don't, we're at risk of potentially doing something that will lead to an infinite loop. So the algebra we need to add to solve our problem is to say, if we're looking at a number that's not a perfect square, we have to find a way to stop, right? We don't want to guess something that's infinite. This is guess and check. So we need an exhaustive set of potential solutions. So
Wait, let's just make a program based on it. So let's just make program. Okay, I understood. I understood the algorithm. Let's just, so x is basically our input integer, which is going to be our input, and enter a number or check. All right. Now our guess starts from 0. So for I in range, it's gonna start from 0 for obvious reasons, and it's gonna end till x plus 1, and our step function is 1. And now we're gonna check if I square, so I raised to power 2 of what we do, yeah, I square equals the input. Okay, if that's true, then print x is a perfect, x is a PAR, perfect SQUARE. Else, if the condition does not get satisfied, else check if, else check if, wait, no. How are we going to check this condition simultaneously? Let me think of this. So it's not. So it's check. It's gonna check if you know, I square I square is less than equals x. If that's the condition, then it's gonna break. It's a perfect square less than equal to, wait, no. Let me just see how my code is gonna work. Let me just take a screenshot of this. I'm gonna paste it over here and I'm gonna see how it works. So, you know, I always love to test the code on a pen or paper. So let's say my x is 1. No, not 1. Let's say my x is 5. Let's not just take 5. Let's take x equals 4. So for I in range, it starts from 0. So I equals, it will start from 0, 1, 2, 3, and then 4. Okay, so when I is 0, it's going to check for the condition that that says check if I square means 0 square is less than equal to x, which is 4. So it's true. Okay, in that case it's going to print a perfect square, so that would be incorrect. So there should not be a less than sign over here. There should be a equality sign. Okay, equal, so that statement is false. Okay, so it's not gonna get inside this. Okay, all right. Check if now. Okay, now it's gonna check since this particular condition is not satisfied. It's gonna move to the next condition, and the next condition is either I square is less than equal to less than equals to x. If that's the case, okay, I guess I've just done the perfect. Let me just erase this all the shit that I did. Uh, okay, wait. So let's say x equals 4 for I in range. So I equals 0, 1, 1, 2, 3, and 4. All right. So it's going to check for the first statement whether I square means 0 square equals x. So it's not. So it's going to move on to the next condition, which is this condition. So next condition is I square, which is 0 square is less than equals to x. What is x? X is our 4. And that's, yeah, it's okay, wait. That condition is satisfied. That condition is satisfied is greater. Okay, wait. So I need to change simple thing. So if it becomes greater than equal to, okay, greater than equal to, greater than equal to, so again, this specific code, this condition is not going to satisfied if because the 0 square is not greater than equal to 4, and it's gonna move again back to the loop. Now it's gonna check for 1 square equals to 4. That condition is again false, and 1 square is greater than equals to 4, so that's again incorrect. 2 2 square equals 4. It's a perfect square. And okay, I have to add a break statement over here. Because once it's a it's a perfect square, I need to get out of my loop, and it's not a perfect square. So print is not a perfect square. Okay, let me just enter CLS, clear this up. I'm gonna run this up, and I'm gonna enter 16. So 16 is a perfect square. Okay. 169. 169 is a perfect square. I'm gonna run this again. Let's check 12. Is not a perfect square. Oh my god, my program just worked. I am glad that I'm able to think of algorithms. Oh my god, I'm just so happy. I'm just so happy.
We're going to use algebra, and we're going to say we're going to stop as soon as our guess squared.
So if you're someone who is initially learning Python, I would definitely recommend doing the checking the code over the paper, because if you check the code how it works, you're gonna get the core, the real logic behind your algorithm, and you'll be able to identify any mistakes. Okay.
Becomes bigger than x. Okay? So we're going to start guessing 0, then 1, then 2, then 3, then 4, and at some point, that number, that guess
So
squared,
let's
will be
say
bigger than x. And we know we can stop because
let's say um let's say 121 is a perfect square. A1 is a perfect square. Let's check 10. 10 is not a perfect square. Let's say 3. 3 is not a perfect square. Let's check 9. 9 is a perfect square. Yeah, it works. It works.
numbers bigger than that will definitely be bigger than x. So our first guess would be 0 squared, obviously less than 10. 1 squared less than 10. 2 squared less than 10. 3 squared less than 10, right? That's 9. 4 squared becomes 16, and we say this is where we stop.
Yes.
And we have not found a square root for 10, right? So 10 is not a perfect square. Does that make sense?
I don't know why my gut feeling says that it's probably not the most efficient or the most optimized program or the algorithm for finding a perfect square. I believe my intuitions tell me that there must exist some better optimized algorithms for finding a perfect whether the given input is a perfect square or not. Okay, let's see. We'll see that in future.
All right. Okay. So our exhaustive set of potential solutions is 0 through 4, because that brought us closest to 10, and at 4 we've gone over 10. And we don't need to check 5, 6, 7, because it's definitely not going to be, those values squared will definitely be bigger than 10. So this is the code that solves that problem.
Okay. Okay, this is not what my code looks like. I'm gonna ask Gemini. The image that you can see from VS Code is mine and the image from the SS MID 6.100L is from the professor. What's the difference in her code and my code? But you are controlling the flow of the program differently. Okay, the fundamental difference boils down to the professor uses a while loop to find stopping boundary while you uses a. Okay, here's a detailed breakdown of how your code compare in efficiency. The professor's code is very specific job. Keep incrementing the guess as long as square its square is strictly less than x becomes equal or greater than to only your code here generates explicit sequence of number from 0 to x instead of letting the loop condition handle the stopping potential naturally. You check the two conditions on every single iteration. Okay, killing the loop manually with a break when either threshold is crossed. Your code is fully functional, but it contains some minor logical redundancy on line 52, okay, and 55. Our condition, if I square equals, since the greater includes your second if statements cover both, it would technically satisfy because of a break statement on line. You never reaches the line when a perfect square is found, but you could just simplify your logic to as a perfect square break, just a great enough here. There is no structural advantage to the professor's approach when it comes to memory and performance on every large. There is one structural advantage, okay, to the professor when it comes to the memory and performance on a very large number input. Guess equals 0. Computer only handles up to your code. Is memory in modern, okay, your code evaluates in memory Python is memory efficient because it does not create a whole list in the memory at once. However, conceptually, your instructor want to run a billion times if it doesn't hit a break. Fortunately, because uh, your second if condition triggers a break the moment I2 exceeds x, your also terminates around, meaning both codes perform roughly the same number of math operations in practice. So your solution is a great command of using a break statement to alter control flow is completely valid. So which one is better? So I'm asking you, which one is better? Don't sugarcoat things. Just let me know. Let me know the REALI too. Just let me know the reality. So I'm asking you, which one is better? Don't sugarcoat things. Yeah. To give the raw reality regard, the professor code is strictly better. Value code works. Okay. You use a for loop. Exactly. Finding a square root is entirely conditional. If you don't know how many guesses it will make until you find the boundary, forcing a for loop to go from. Then using two manual break statements to get really trying to handle a graph while loop. Code duplication and maintenance. Look at how many times you have to write your point statement and break. You have to separate two break statements if you want to. Okay, redundant now on line 51, the code calculates exponent to the on the line 52 it runs the exponent math twice up the loop iteration. The professor checks whether the guess is less than x once per turn. Lyron uses fewer operations. If you submit a code on a pset, it will pass the autograder because the output matches. But if you write your code like in a midterm or a technical job interview, it signals you don't fully understand when to deploy it. Oh my god. Okay. Okay, that hurts for some reason. I don't fully understand when to deploy a while loop versus a for loop. Okay. Okay, let's see what the professor is saying. So guess equals 0. The x is input into an integer while guess square is less than x. We're gonna add guess into we're gonna increment the guess variable. If guess, then it's what it's gonna do is check if okay, all right. So it's going to check if the guess square is equals to x, else prints it's not a perfect square. Okay, all right.
We get input from the user. So what number do you want to find whether it's a perfect square or not? And what is it if it is a perfect square?
37, 31, 37, 31, 37, 31. My code for this PROBLEM. I'm just gonna check.
We have a while loop that checks one
So I'm gonna comment down the code. Yeah.
condition, right? That's our stopping condition here. We're going to iterate through the loop when guess squared is less than x, right? So on that number line, we're going to keep incrementing by 1 as long as our square is less than x. So that's this while loop here.
Exit when
And
guess
what
square is greater than or equal to 2.
we're doing inside the loop is
Okay, so I totally understand why it's so let's say it's 10, so let's say x is 10 and x is 10, our guess is initially 0, so 0 square is less than 10. Yeah, less than 10. It's again gonna add 1 square is less than 10, 2 square is less than 10, 3 square is less than 10. So but when our the loop variable gets 4 square less than 10, it's gonna break. It's not gonna satisfy. So it after this, it's gonna break. It's gonna come out of the loop and it's gonna step to the next if guess square. you know so 3 square, which is 9, it's not equal to and mathematically that's not equal to 10. So it's gonna jump to the else statement is not a perfect square.
incrementing our guess, right? Guess equals guess
I get
plus
it.
1. And then at some point, if we haven't found a perfect square, or if we have found a perfect square, this condition becomes false, right? Because this is false when we have the opposite of this less than sign. So guess squared becomes greater than or equal to x. Now that's two very different things, right? Guess squared greater than x means we haven't found this perfect square. But guess squared is equal to x means we have found a perfect square.
A perfect square.
Right? And both of those cases trigger us.
Let me see if I'm recording or not. Am I recording? Yeah, that looks perfect. Oh, that's another hour. I think I need to eat something, so I'm just gonna pause this lecture right now. I'm gonna eat something and I'm gonna get back within what time it is. So it's 7:14. I'll probably get back at 7:45. I'll definitely get back because I have to complete this lecture 4. I know it's quite a long lecture, but I have to do it anyway. Alright, so I'm back, and yeah, everything looks okay, and I'm just gonna uh, continue with where I was.
Perfect square, right? And both of those cases trigger us to leave the while loop. So then, right after the while loop, we need to have an if-else. The if-else checks for one of those two cases. So the if guess squared is equivalent to x means that we exited the
So in this particular code, I made my own code. Eventually, I was getting the same output as this code gives, but that the lecturer, the professor, the code given by the professor is way more efficient because it initially what it does is it basically checks if the guess the square of the guess is less than the input value, which is our variable x, and then it checks whether uh, whether if it's the square root of the given input or not, or based on that it tells whether if it's a perfect square root or not. And yeah, so that was it. Yeah, that pretty much that was it.
the while loop because we found that it was a perfect square. So like 4, for example, right? If x was 4, when we hit 2, that while loop becomes false, and we exited because 4 was a perfect square. But the 10, for example, would fall within the else clause here, right? Because we have exited the loop because guess squared 4 squared 16 was greater than 10.
Yeah,
Okay. And so
exactly.
then we would print x is not a perfect square. Okay. So this works for many different values, as big as you'd like, but it doesn't work for negative values. And the reason it doesn't work for negative values is because the loop never actually enters in the first place. So for example,
Exactly.
if we look at this, whether -2 is a perfect square.
Wait, -2 is a perfect square. Mathematically, that's not possible because you know we are basically saying that we have given a number x. Okay, my bad. So mathematically, we have given a number x whose which is a perfect square, and let's say it's negative of 2. That's not possible because if we find the value for x, we would get uh, the under root of -2, which is nothing but uh, I guess that's iota times root 2 plus minus iota times root 2. Uh, that's not a real number. That's not a real number. So this particular value in this case, x does not belongs to real value. Instead, x belongs to complex number. And I think in order to tackle or in order to handle complex numbers in Python, we do something different. As far as I remember, we use some libraries or we use some functions to deal with complex numbers in Python, but I think we are not doing that right now.
We're going to start with guesses 0.
This slide particularly says that could check for the negative input and handle differently. Okay.
Because that's how we implemented the algorithm, right? On the previous slide, it says guess is equal to 0 right at the top. And so guess is 0, we say, is 0 squared less than x? No, 0 is not less than -2. And that while loop never even enters.
So 0 is greater than 0 is mathematically 0 is greater than negative of 2. So we never enter the loop. Wait, where's the code? So there it is. So it never enters this loop because our guess is 0, and our guess is 0 square initially, and x is negative of 2. So this the this so boolean value for this condition is false, so we never enter this particular loop, and we eventually moves on to this. Okay. So then this condition also does not get satisfied, and we move on to the else condition, where it just prints that x is not a perfect square. So this code even works for negative numbers. Wait. So guess was 0. 0 square equals, so this condition would be false, so we never enter this condition. Okay, and we eventually print x, which was in our case is negative of 2, is not a perfect square.
At all. Which is fine, right? Because -2 does not, or -4, negative numbers are not perfect squares unless
Exactly.
we're talking about imaginary numbers.
Imaginary or complex numbers.
But we're not in this particular case. However, we might want to handle the case when the user gives us a negative number. Maybe they accidentally typed in the negative sign or something like that.
All right.
So we can actually take care of that case by adding a little bit of extra code around what we already wrote. So the stuff that's...
So negative flag equals false if x... Wait, so it says that enter a positive number. If x is less than 0, negative flag equals true. So initially it was false, then it becomes true. Wait. If true, okay. So here the variable, not the variable, but this, what do you call this? This negative flag gets the value for true if x is negative. So let's say if I enter negative of 2 or negative of 4, so it's gonna this block of code is gonna execute, and it gonna says negative flag negative flag equals true. And then when we enter when we reach till the end of the code, uh, it's just going to give us output that just checking, did you mean negative of x? Okay, so it's basically trying to correct the user that you have given an incorrect input. That's what all we are doing over here.
Boxed in red is the extra code we write. Everything else is exactly the same as 2 slides ago. Okay. So the only thing we want...
And let's say if I enter positive 4, so positive 4, so positive 4 is going to skip this, because this, in that case, this condition is going to be false, because x 4 less than 0 is false. So we are not going to and then this thing is actually going to be false by default. So if this statement is false, this print statement is not going to execute.
What we want to do when we encounter a negative number is flag it using a new variable that's either true or false.
So it's not a rocket science. It's a very easy basic program, I think so.
False. And then at the end we can handle that flag. So if it's true, we do something, and if it's false, we do something else. Okay. So in this particular case, we've got a negative flag initially false, which means that we're going to initially assume the user gives us a positive value, right?
But by putting these by putting negative flag equals false, that's a very pretty clever thing that we have done initially. So whosoever wrote this code was quite clever.
So negative flag equals false. We get input from the user, and then we check if the user gave us a negative number. So if the x is less than 0, then we're going to change the value of this flag. Neg flag equals to true. Right? So we're going to change the value from false to true. And then the rest of it is the same, right? This is all the same as what we had 2 slides ago, except that at the end, we're going to check to see if the user actually gave us a negative number we can check with them, did you actually mean the positive version of that number or something like that. And so in code, the way this looks is as follows. So if we run it and we give it, 4, obviously it tells us it's a perfect square and what its square root is. 9 works. 10, it says it's not a perfect square. And then when we give it a negative number, square or not, it just tells us -4 is not a perfect square, and then it says just checking, did you mean 4? So it does this extra print statement when the number was negative. Yeah, question.
I didn't quite get like the negative flag equals false.
I didn't quite get the inaudibles.
Yeah, so I can explain that again. So the negative flag equals false is just a variable, right? I just called it neg flag. It's a variable I initialized to false just to say, hey, the number I'm going to assume is not negative. And then we only flag it to, we only change its value to true if the number was negative. So in fact, we could have just had a
So again, that's a very clever thing to do.
little if else here, right? So we get the x, we don't have this line up here. We have x is equal to int, and then we say if x is less than 0, neg flag equals true, else neg flag equals false. We could have done that as well. Yeah. Okay, so the big idea with guess and check is we can't test an infinite number of values. We have to stop at some point, right? So now we've been working with the code that looks like something on the left side, right? We've been using while loops, but we've seen that we can actually write very efficient code using for loops as well. And in fact, the guess and check method maybe intuitively lends itself better to a for loop than a while loop, right? Because we're trying to iterate through an exhaustive.
So using while loop, so that's the initial guess. Is your guess correct? If it's no, then we are going to guess it again. Choosing the next guess. If the condition gets true, then we are going to break the loop. Similar is somewhat for the for loop. So sequentially goes through all the possible values and it checks whether if it's correct or not. If it's not, then it goes again through sequentially goes through all the possible guesses, and if we get you know uh, if we found our condition to be true, did not find a solution. Wait, why does it say that it did not find a solution?
Set of values, right? The number 0 through some number, right? And so maybe a for loop is a better way to write such a guess and check algorithm. And we're going to see how to rewrite that in a little bit. But in terms of a flowchart, the way the for loop would go is we sequentially go through all the possible values. When we've exhausted all the values, we say we didn't find a solution. And otherwise, the for loop just automatically grabs for us the next value in the sequence.
Okay, so what it says that hard-code a number as a secret number. Okay, number is a secret number. So Sn, I'm gonna name the variable as Sn. Write a program that checks through all the numbers from 1 to 10 and prints the secret value if it's in that range. If it's not found, it doesn't print anything. Okay, so let's say let me just comment out, and let's say our S secret number is basically 20. Okay, that's my age. Write a program that checks through all the numbers from 1 to, so we're going to use the for loop for I in Sn. So it's gonna go through all the values. Wait, let me just read that question. So gonna check through all the numbers from 1 to 10 and print the secret value if it's in that range. Wait, so it says that write a program that checks through all the numbers, all right, and prints the secret value if it's in that range. It doesn't print anything. what we need over here is um, oh, what's wrong with my antivirus? Okay, so for x in range, we're gonna start with 1 till 11. Okay, and then x becomes x is equals to x plus 1. uh, Print x. Okay, so let me just run the code. Print I. So int object is not iterable. Um, Wait, let me just move on to the question once again. How does the program look if I change the requirements to be if it's not found prints that it didn't find it? What do you mean by that? So listen. So what it's the problem is saying is that we have a secret number. Let's say it's nine. It's not nine. Let's say it's seven. Okay, we have a secret number 7, and we have to write a program that checks whether this number 7 is present between the number 1 to 10. If it is present, so we are going to get, so let's make a condition, a condition box over here. So secret number in our sequence, if it's true, if it's true, then it's gonna print that number. And if it's false, so it's gonna check once again. So I have to make a box over here, check again. I think we can do that easily. If it's false, okay. um so how can we do that? Let me think. Okay, let me think. So let's say our secret number is 7. For I in range, we're going to start from 1 to 11, and then check if I equals that secret number. If it's true, then print our our secret number is, so it's basically SN. Okay. Else, so else pass. Okay, let's check. Let's just test our code, not on the VS Code, but on the paper itself, if it works or not. So I'm just gonna paste it over here, and okay. So here's I. It's gonna start with 1. Check if 1 equals 7, so it becomes false. It goes over the else statement, it passes, and then it goes over the for loop once again, and then the value for I becomes 2, and the condition would check whether if it's 2 equals 7 or not, and it does until I get I equals 7. So in that case it would be 7. This condition becomes true, and it just prints that this our secret number. So let's just run this program. Our secret number is 7. Let's just change that secret number to be 20. So we should not get any output. We got nothing. That's what the program said. If it's in that range, if it's not found, it doesn't print anything. Okay.
So let's have you work on this for a little bit. I want you to hard code for me a number as a secret number. This is kind of what we did last lecture. So secret equals, 7.
I think that's a pretty easy question, or either I am doing something wrong. Possibly.
And 5, whatever you'd like it to be. And then I want you to write some code that goes through all of these numbers from 1 to 10 inclusive, let's say, and
Okay.
prints that it found the secret number. So if the secret number is within the range 0 through 10, print that you found the number. And otherwise, don't print anything. So if you don't find the number, print nothing. And as you're working on that, and if you finish that code, think about how you would change that code to do one thing differently. If it's not found, print that you didn't find it.
So, okay, else print we didn't find it. Wait, what? Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I think I need to use a break statement. No, 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 wait. If I use a break statement, our program will get break, and that's not a good thing to do. Um, okay, wait. Else pass. I think it should work now. We didn't find it. And if I try to change the value of, no, wait, that's not, oh wait, I just accidentally moved my camera. Let me just, yep, that's perfect. Let me just adjust my camera for a second. Okay, yeah, that looks perfect. So, where was I? Yeah. So I can't just put this over here, because if I do, then we are going to get, we didn't find it as an output every time we run our program. So else, I need to think of something else. Let me think. Let me think. So, uh, you know, we get into this condition. We got into this condition whether we see whether if it's okay. If I put a break statement over here, it won't do anything much. Yeah. Okay. Let me just put it to, let's say, 9. Let's say our secret number is 9. And else, oh wait. That's a really good question. That's making me think. So it says, if I afterwards we have to change, we have to do a minor change in the program, that if it's not found, then it prints that it didn't find it. So um how do I avoid this? How can I avoid this? Let me think. Okay. All right. So I've actually thought of one thing. So let me just clear this up. Okay, I have an idea. Okay, I have an idea. So let's have a secret number. Check if the secret number is less than equals 10, and it also checks if the secret number is greater than equal to 1. So mathematically by using this if statement, we are actually verifying that our secret number, which is Sn, belongs to 1 comma 1 comma 10 in the closed bracket. So if it's in that range, it's going to print that it's in the range. Else it's going to print not in the range, not in the range. So here we are talking about range, and uh, there's actually one more thing to notice about this problem, that it's not uh, given, or it's not mentioned over here that we need to use for loop or while loop in particular to solve this problem. So let's just try to run our code. It's in the range, so let's try to put 11. Not in the range. I don't know if they're going to use loop for this or not. Let's
So in the
let's
first
let's
version,
just
if
see.
you don't find it, do nothing. But in the second version, if you don't find it, tell me that you didn't find it. Okay? So these codes are in this Python file, and the easier version is about line 129.
So our secret number, that's 4. So let's just put it to 4. Yeah, that's it. Let's run it. It's in the range. That's pretty obvious.
And then if you work on, after you finish that, if you're done, you can just copy that code to lines about 144 and try to modify it to the new specification. So if you don't find it, print that you didn't find it. Okay, so tell me some code for the first one. So if we find the number, print we found it, and otherwise do nothing. What's better, while loop or for loop?
Okay, so they are indeed using loop over here, but I don't think that we need to use loop in this case.
For loop, yeah. For, let's say I, in range. How do I get numbers 1 to 10 inclusive?
So 1 comma 11.
1 comma 11, exactly.
Exactly.
Good. So this, and again, I can.
Okay. So I'm just gonna write down that timing. Let me just get my rough notebook. Just give me a second. Okay. What's the timestamp? That's for 6:17. All right.
write a little message for myself. I is 1, 2, 3.
Okay.
4 dot 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 11. What do I
No,
do to make the check whether this number
no,
I
it's not 11. It's 10.
is my secret? Yep, if I equals secret, let's say print found. Okay, run it. Obviously 4 is within that range. Obviously 100, not in that range. Right? So
Not
when
in the
we had 4, it
range.
printed found, and when we had 100, it did nothing. Okay,
We have
I'm
no
going to
output.
copy this code and paste it down here. So let's try the version now where we just make one small change to our specification, right? Now we request the code to say if you don't find the number within this range, print that you did not find it. What are some things we can try? Else, okay.
But if you're using else, it's just gonna repeat Not found, not found. Over 10 times.
Print
Not found.
not found. Okay. So
So that's a bad program.
4 obviously
Oops.
was found, but we also printed all these not founds. Why? Yes.
It's iterating through the whole range. So you could try maybe breaking out of the for loop.
Why? Yes.
It's iterating through the whole range.
Wait, why don't I see captions? Okay.
So you could try maybe breaking out of the for loop.
Yeah. We printed it because it's iterating through the whole range. Every time I check an I, I'm either printing found or not found. Yeah. So we could break, I guess, when we found it, right? Break. Run it.
But we're still gonna we somehow need to satisfy this condition only if it's not found, but even if we are not, even we are founding, this particular condition is getting satisfied.
Okay, then we print not found until we find it, and then we break. So we're getting there, right? It's looking a little bit better.
Yeah, it does.
What else can we try? Yes. Another break?
No, no, no,
We can
no.
try another break after not found.
No, it's completely gonna break the program itself, so our algorithm will not work.
But then the 4 is not found.
Oh,
Yeah.
which is a logical error, I guess.
Range, but I that's in range 1 to 11. Sampling has match, of course. Then it's true that we like in the end, at the end of the script,
I don't know what they're saying.
Yeah. I like the idea. Yeah, you can try to do a Boolean flag. Was that your suggestion as well? Yeah? Okay. Let's try to do the Boolean flag way.
Okay, Boolean flag, but okay, okay.
Let's delete the breaks. Let's go back to what we had before.
But what about this, man? What about this? That's the simplest, and the cleanest code that you could ever write. But anyways,
So basically, our idea is, I think, what we're trying to get at is we only want to print not found when we've gone through all the numbers in the range, right? So kind of something like this, right? I want to print the not found only once at the end of my loop.
okay, I get it. So I get it. I totally get it. So for I in range, so we're gonna start from 1 till 11, and our step function would be 1. I'm just gonna habit of writing the step function itself. If I equals sn, which is our secret number, it's gonna print what? So it's gonna print found. Okay, and let's take a variable, and we initialize the variable with a equals true. Okay, and then we break over here. We break our loop over here if we found, and if we didn't found, else put the value for a equals false. So now we're going to put another. If a equals uh, false, equals false, then we're going to print not found. Not found. Let's just test this our code in the notebook. um, Not pretty sure if it's gonna work or not. So let's see. So our secret number is 4a equals true. For I in range, it's gonna, so I is again gonna start over 1, 2 till 10. And when our I becomes 4, when the value for I becomes 4, this condition is gonna get satisfied. So we'll get found. Otherwise, if our condition is not satisfied, it's gonna get to this else statement, and it's gonna initialize, not initialize, but it's gonna bound the value of false, which is a Boolean value, to a, and then it's gonna get out of the loop, and then it's again gonna run the loop until our if condition gets satisfied. So let's say we don't have 4. Our secret number is not 4. Instead, it's let's say it's if it's 20, that's my age. So this if condition never gets satisfied because our secret number is not in the range. So this block of code will never run, and it's gonna get else. So we're gonna set a equals false. Okay. Okay, and just because our I, the value, our, the loop variable has reached its maximum value, which is 10, it's going to get out of the loop. And when we got out of the loop, we had the value for a equals false, and this condition over here is probably going to check what's the value for a. So it checks if a equals false, and which is true itself, and then it's going to print that it's not found. So okay, so I just made the correct program. Wait, it says found, not found. Okay, I think I did some mistake over here. Why it says if a equals false. um so it's 4, okay. you know Wait, so a was false if a, I think it should be just a. If a found, okay, let me just change the variable for our secret number. Let's keep it 20. It says not found. If okay, it should be, I guess I should I should change the value to be true, and I should initialize the initial value to be false. Let's see. Okay, let me just run that. Not found. Let me just check for one. Found. Okay, so let's just, what I did here is basically a hidden trial, but I'm gonna, look at the logic behind this, or I'm gonna look at the algorithm behind this particular code. So our secret number is 1, and we are initializing a with a Boolean value false for I in range. So again, we start over. So 1, this condition gets satisfied, and we get the output as found, and then we break out of the for loop. That's it. And if true, so if false, so this particular block does not even get executed because this statement is false, so we don't even get this as output. Let's see a case for a very or for a secret number which is not 1. Let's say it's 20. uh okay, so this particular block is never gonna get executed. So I'm just gonna raise this up. So it's gonna get to else a equals true, and then it gets out of the for loop because we have reached the maximum limit for our uh, loop variable, and then it's gonna jump to this particular if statement if a. Now the value for a has been overwritten by this command which is in the line 67. So instead of a equals false, now it's a equals true. So if true, so that's a true statement, it's going to print not found.
Okay? But this code doesn't work either.
Okay, so that was really, really interesting, using Boolean, Boolean method, we could eventually solve these types of uh, problems in Python, and that's a profound way to solve problems. Yeah, I really loved it.
Either.
I'm probably gonna write that in my notebook in case, you know, in future I would be using the Boolean method. So I'm just gonna write a note. We can use Boolean method to solve many problems in Python. Yeah,
Because
that's it.
I'm always printing not found. No matter if I do this extra print inside here, right? Because this not found at the end here is at the same indentation level as the for loop. So the suggestion from a couple of you is to actually set a flag.
Solving problem in Python, particular feels like more like a hit and trial instead of building an algorithm which directly works in the first go.
Right? So we can set a found flag to be originally, let's say, false, right? So before I even start my loop, let me just assume it's false. And I'm going to use this flag to trigger, or I guess I'm going to change this flag whenever I found the number, right? So found is originally false, and the place in my code where I know I found the number is here, right? When I is equivalent to my secret. And then I can set my found flag to be true. I only call it a flag because it flags that an event happened or not, so it's kind of a Boolean event. But it's really just a variable, right? Nothing special about the word flag, it's just a variable. Right? Okay, so now I think the suggestion was, now that we've set our flag to true or false, depending on what happened in the code, we can say if found, or I guess in this particular case, if not found, right? The inverse of my Boolean, print not found. Right? There's no else, because the else was already taken care of when we had the secret, when we found the secret within the code. So now we print found when it's 4, and if the number is obviously outside the range, like 100, we print not found. We can make a small change to it, I guess, so we don't have to print found down in there. For maybe consistency or making things even, we can just say else print found or something like that. And I think that should work as well. So 100 is not found, and 4 is found. Right?
Yeah.
So now we're doing things kind of consistently. We're printing out whether we found it or not down here, and inside the for loop, we're just dealing with the logic of the finding or not finding it. Any questions about this code? Does it seem all right?
It's
Does
pretty,
it make sense?
Yeah, it makes sense.
So,
It's pretty clear.
I'm showcasing these Boolean flags just because they're very useful for signaling that things happened in your code. Right?
Okay.
So when you find yourself asking, how do I know?
So, I don't know why it might be, it might sound a little bit of weird, but it's like somewhat working of a transistor, you know. I don't exactly remember how a transistor work, but I do remember that, by using the middle leg, I don't know what it's called. I think Um, you know, I think it's called. I don't remember exactly. Wait, let me search for it. Uh, diode, not a diode. Transistor. Exactly. So we do something in the base emitter and the collector. We send some sort of voltage to change the electrical, to alter the electrical signals. This I'm just relating it to the Python. uh, Using Boolean method, we could actually alter, or we could just signal something in our code to change without messing up with the actual logic of our algorithm. And that's pretty crazy.
Know that this thing happened or something like Boolean flag is the answer, right? Just set it.
Let me just ask the same thing to Gemini, what it says. So I learned about the Boolean method, where you signal signal something in the code without changing the algorithm uh, algorithm changing the logic of algorithm in the lecture 4 or 6.100L. uh, I just so a random thought came in my mind that it felt like to a function of a transistor that I as to you studied in physics, even if I don't remember, I mean, REME, and remember how it used to function. What do you think is somewhat similar to using the Boolean Boolean method in Python? And okay, so let's see what it says. You have a fantastic intuition. You're connecting the software concept straight back to the hardware engineering that makes computer work in the first place. Your random thought is actually on spot on. A Boolean flag in the Python operates on the exact same fundamental philosophy as a transistor in physics. So that's pretty crazy. Okay, that's pretty crazy. Uh, Let me just scroll down in the lecture. Boolean flag that found is equals false. Used to signal or remember something that happened, changing how the rest of the code behaves without altering the core loop math. A transistor does the same exact thing in the physical level. It's a tiny semiconductor switch. It takes exactly. If the voltage is present, the transistor opens up, allows the large current to flow through. And if the voltage is absent, the transistor blocks the current completely. Just like your Boolean variable signals the code to change the direction of physical transistor. State keeping memory in a Python code, a Boolean flag allows the computer to remember. For example, I was looking for a perfect square. Exactly. So I found it. So it will play found to be true. Okay. So just a random and a analogy came into my mind about this relation. Okay, exactly, exactly. So abstraction. Okay, So
Into
let's
true
just
or
continue our
false,
lecture.
0 or 1, A or B, whatever you want, and then check the value of that variable.
So honestly speaking, that's a really interesting thing that I've learned today in the lecture 4. I can't imagine what I'm gonna learn in the upcoming lectures.
Later on in the code to see if the event happened or not.
Okay, so we are actually given a you try it code. So what it says, compare the two codes that hard code a number as a secret number. All right, checks all the numbers from 0 to okay. All right, if it's not found. Okay, so it's basically the solution, I guess. It's actually a solution for the previous problem that we did.
These are the two codes that we had just written, kind of side by side, just to show you exactly what the difference is. So here is the code where if we don't find the number, we don't print anything, right? So it's just the for loop with an if, and we say we found it. And the one on the right is the code where we did find it, where if we didn't find it, we printed that we didn't find it. So the only things that are added in addition to the code on the left is the stuff that's bolded, right? So I just have this flag that I initially set to false. I set it to true when this event happened. That is, I found the number. And then I do the check at the end to print or not print found. Yeah.
Can you explain why you don't use else when the value is code?
I don't use else in the if or down here? In the if? So we don't use the else inside the if I equals secret because that if or else will be done every time through the loop. Right? And I only print that we didn't find it one time at the end, right? If I have an else inside the for loop, it's basically asking if I is the secret number. So 0 is not the secret number, we would hit the else. 1 is not the secret number, we'd hit the else. 2 is not the secret number, we hit the else. And only when I get to 7 in this case, it is the secret number, so I hit the if, and so on. So it's not something I want to do every time through the loop, I put it at the end because I only need to do it once.
Okay.
That make sense?
Yeah, that makes sense.
Okay. So Boolean
Booleans can be used as signals that something happened. We call them Boolean flags. So I'm just gonna write down. It's called Boolean flags. Honestly speaking, this is probably something that I never studied in my high school, and even if I would have studied in this in my high school, uh, they never mention about something called Boolean flags in Python.
variables are a
So it was a great experience learning about this.
variable that is in one of two
Wait, how much of a lecture is left? 18 minutes.
states, right? I used here true or false, but as I mentioned, you can use 0 or 1, A or B, as long as you as the programmer remember what values you're expecting this variable to take on. Boolean variables can be used as signals that something happened in the code, right? So this could be useful in a quiz situation. We call these Boolean flags, but again, it's just a name. It's just a variable that changes state depending on if some event happened in the code. Okay, so I'm coming back to the idea of while and for loops, and we've already seen that.
While loop or for loop. So already saw the code looks cleaner when iterating over the sequence of the values using a for loop. So don't set up the iterant yourself as with a while loop. Less likely to introduce errors. Consider an example that uses for loop. For loop and an explicit range of values.
There are many situations where for loops are a lot easier to use than while loops.
So they're actually recommending us to use for loops over while loops because when you do iteration, there are less chances of errors. Uh, you know, and we could explicitly uh, change the range of the values for, let's say, if instead of starting from 0 we have to start over 5, and let's say if we want to step over the function, instead of using just by default, which is 1, instead we can use 2, 3, or whatever we want to use. So I think that puts us over into something, which could be more optimized and more uh, uh, there's actually a term for it. I don't remember that term. Customizable. So that's more customizable as compared to using while loops.
Okay. So when we have for loops that iterate through a sequence of values. So the guess and check algorithm actually lends itself a little bit better to for loops than while loops. So here's an example of us trying to find the cube root in this particular case, not the square root of a number. And again, we're only asking.
So cube is that's our input. For guess, cube plus 1. So for guess in range, so guess starts from 0. So 0 cube. My bad. Yeah, 0 raised to power 3 is 0 equals. So this statement is false. This particular statement gets false initially when the value for the guess is 0, and okay, and we're gonna get loop again. Okay, and the print the cube root of the. Okay, I get it. I totally get the point of this code.
If this number x is or in this case cube, is a perfect cube, okay? So the way the code works with a for loop is we're going to iterate through all the possible values. So we have for our guess in range some number, so we're going to check all the values 0 all the way up through cube plus 1. The reason why we did the plus 1 is because if the user gives us the number 1,
Exactly.
we want to check 1 itself, right? If we didn't have cube plus 1, if we just had cube, we would mistakenly stop at 0, even though 1 is a perfect cube. Okay, and then inside the for loop, we just have if guess cubed is equal to cube, then we have found our perfect cube. Okay? If we have negative numbers with cubes, it's just adding a little bit of extra code, but
So
hey, the number I'm going to
oh,
assume is not negative.
oops, my bad.
Again, we're only have all the because we have a cube root of a negative.
So what's ABS function in Python? Absolute value. Okay. So all right. Okay.
Negative number is just the cube root of that positive version of that number with a negative sign in front of it. So all we're doing with a negative number as the input is saying I'm going to iterate through all these values through 0 all the way up to the positive version of whatever the user gave me. So this is taking the absolute value of the number the user gave me and adding 1 to it. So just kind of like the code on the previous slide, except we're doing the absolute value of it. We're checking if the guess cubed is equivalent to the absolute value of cubed, exactly the same as on the previous slide, except taking the absolute value of the cube. And then we have this extra little bit that checks if the user actually gave us a negative number. So do we need to put a negative number in front of our guess? So if the user actually did give us a negative number, let's just do minus whatever value we just found for the cube, and then we can print the cube root of this perfect cube. Okay, so again, same code as before, the only difference is absolute value of cube and adding this check to deal with negative numbers. Okay, so we can actually make this code a little bit faster because, for example, when we're checking the cube root of 27, the numbers we're checking are 0, 1, 2, 3, 4, 5, 6, in our for loop all the way up to 27, right? But we can recognize the fact that when we reach, 27, fine. Let's say 26. We can recognize the fact that when we hit 3, The guess cubed is actually 27.
27. Exactly.
Right? And so in our for loop, it doesn't make sense to keep checking 4, 5, 6, 7 to see if those numbers.
So that's one of the reason that that code that I wrote, using that, where I was comparing, just a few minutes or hours ago, where I was comparing the code given by the professor and the me. That was the main issue. So my code was checking over all the numbers once over again and again, which would have taken a time, even though it does not seems to like, but the computer does take time in milliseconds or fraction of second more, uh, with respect to the code that the professor has written. But in their case, they're just saying that, let's say you have just got the 3 cube, which is 27, then our program or the algorithm won't check for the cube for the 4. So it actually saves time and memory.
Are then going to match or be our cube root for a potentially perfect
So
cube.
in this case, let's say um, if our input is 26, so that's not a perfect cube.
And so that's what this code is doing. It's going to have a little if statement.
See. So for guess in range, so it starts from 0 and it goes to the absolute value of the cube. So let's say we put 26. Okay, 26. If guess cube is greater than or equal to the absolute value of the cube, um, wait, guess cube. So initially it's 0. 0 is greater than or equal to, that's false. So it's not gonna get execute, and I think it's gonna get loop over this, uh, for loop. Okay, and let's say we reach 3. Okay, let me just put that in my OneNote and see what's happening over here. So here's the thing. Let's say our input was 26. 26. Okay, and the abstract value for 26 is basically 26 itself. Our guess initially, the guess, I'm just denoting it by g, is 0. So g, 0 cube is 0 itself. 1 cube is what? 1. 2 cube is 8. When it checks for the 3 cube, we say it's 27. So we get over here 27, and our abstract value for the cube, that's 26, which is our input. This condition actually gets satisfied, and we move to break, and we come out of this for loop, and eventually we move to the next block of code. So if guess cube is not equals, okay, so that's what they have done. If guess cube, which we got is 27, is not equals 26, which is true because 27 and 26 are mathematically not equal. Print the cube is not a perfect cube, which is true because 26 is not a perfect cube. Else check if cube is less than 0. So this condition will not get satisfied, and we would have just left with this output, that 26, which was our input, is not a perfect cube. Okay, what if our, instead of 26 it was negative of 26? So in that case, we would have looked at this particular block of code. If cube, which was our input, which was minus of 26, is less than 0, which is true. So guess, what is guess? So guess was 27. 27 equals negative of 27. Okay, wait, wait. So the guess, okay, wait, the guess, okay, the guess is not 27. The value for the guess is actually 3. Okay, 3 equals, okay, so that's a new variable, my bad. So this particular variable gets negative of 3, which was our guess value, where we stopped, you know, so because 3 cube is 27, and then it would have just print cube root of str string of cube, um, 3, or cube, sorry, minus of 26 is string, wait. Is there any error in this code? Wait, I think there's some error in this code, because it says the cube root of string value of 26 negative of 26, that would be negative of 26 itself, because negative of 26 was our input, is string value of the guess, which is minus 3, which is not, I think there's some error in the code. I need to see the lecture.
Statement in here. So again, this is the same as before, but we're going to have a little if statement that says if the guess cubed is greater than or equal to, not just equal to,
I think that's a bad code.
but greater than or equal to. Let's break out of
Let me see if I'm recording. Yeah, that's perfect.
the loop. Okay? And so when this condition is false, or sorry, when this condition is true, guess cubed is greater than or equal to, we
It
have
breaks.
exited the loop. But now, just like with the square root code, with the while loop, we have to see why we exited the loop. Why did we break out of this loop prematurely? Okay? One is we exited because the guess cubed was equal to the cube, or the guess cubed was greater than the cube. And so then we have a little if-else conditional here that says if we exited because it's not equal, greater than, then it's not a perfect cube. And otherwise, we exited because it was equal to, which is the same code we had on the.
Okay. All right. My bad. My bad. Okay, so this code is correct. Uh, the point where I got this incorrect is this block of code will not execute if my input is negative of 26, because if we check over here, the guess cube, which is 27, so 27 is not equal to 26, which is true. Then this particular block of code will execute, so it will print that the cube, that minus 26, is not a perfect cube, which is true. Okay, if it if instead, if it would be 27, you know if this condition would be false, then this block of code would have executed. So, okay, it was my bad. I guess it was my bad. So, this code is perfect. This code is perfect. Okay.
The previous slide. Check whether the user gave us a positive or negative value, put the negative sign in front of our guess, and then print the perfect cube root. Okay. So all variations of the same sort of starter code, we're just adding little bits of functionality and making the code slightly more efficient here and there.
Another example. So remember the word problem from your childhood. For example, are selling tickets to a fundraiser. Okay. Less than. Okay. So if I have to write that mathematically, I could have just write it as b. So the value for b, that equals uh, a minus 2, sells twice as many as, so c equals 2 times of a. 10 total was sold by the 3 people, so it means that a plus b plus c should be equal to 10. Okay, so b is basically a minus 2, so a plus b. B is basically a minus 2 plus what is c, that is 2 times of a, that equals 10. And so this becomes 2, 3, 4. 4 times of a is 4 times of a minus 2 is basically 4 times of a minus 2 is 10, and a comes out to be what? So that becomes 12, 3. A comes out to be 3. Okay. If that's 3, then b is 1. If a is 3, then c is 6. So just using these three equations, we could, that's a pretty obvious thing, that if we have n equations and n variables, we could just have find out the value for the variables. How many did okay, a sold, so a sold 3. Could solve this algebraically, but can we also use guess and check? Okay, we can. I did solve it algebraically, but I'm not pretty sure if we can use Python to solve this. Can we make the algebraic equations like this? I don't know. I don't know if Python could solve. I don't know. Like, uh, okay,
So I
let's
have
see.
another example, and this example is probably the point in this class where you're like, aha, this is what computational thinking means.
Okay,
So remember
computational thinking. What's computational thinking? What's Okay, so think of the step before you write a single line of Python code. It's architectural blueprint of the okay, decomposition, pattern recognition, abstraction, algorithmic design. Okay, computers are incredible, but they are completely stupid. My bad. So they only do exactly what you tell them. If you give a big problem like find the best route, it will crash. Is Computational thinking is like a translation. You use decomposition, pattern, abstraction, and algorithm to turn that vague human desire into hyper-specific logical roadmap that a machine can execute in milliseconds. Exactly. Okay.
these word problems from childhood, right? You see a math problem, you have
Yeah.
basically a system of equations.
Exactly.
Algebraically, you could probably solve it within a minute or so. We can actually apply computation to solve problems just like these.
So here's the thing where Python gets really interesting.
So we don't need to do it algebraically. We can just tell the computer, here's a bunch of values I want you to try them to see if they match these systems of equations, and then print out the answer. Right? So here's an example. I've got Alyssa, Ben, and Cindy selling tickets to a fundraiser. Ben sells 2 fewer than Alyssa. Cindy sells twice as many. 10 total tickets were sold. How many did Alyssa sell? Here's some code that could solve this problem for us.
Oh my god. Oh my god. I'm not gonna understand this code by myself. I'm probably gonna use AI. Let me explain this in video. This shit. Okay, let's just try to understand it on our own. For uh for A in range, okay, for Ben in range, for C in range, for B in range, for C in range, total equals down. 2 less equals B minus. Oh my god. Take a deep breath. Nested loop can look like absolute nightmare when you first see them. This code is doing brute force search or executive enumeration. Think of this code like a three-digit combination lock. To open lock, you have to spin the first wheel. Oh my God. So this is probably a new thing that I've studied. I've never seen something like this.
I'm
So
basically
let's just try to understand what the professor says.
figuring out all the possible combinations for tickets that Alyssa and Ben and Cindy could sell, right? So I've got 3 loops, each nested, right? So Alyssa could sell 0 or 1 ticket or 2 tickets and so on, but for every value of Alyssa. So Alyssa can sell 0, 1, or 2 tickets. For every one of those, Ben can sell 0.
Okay, all right. S- don't tell me that we here we are using permutation and combinations. By using this equation that a plus b plus c equals 10. There can be multiple permutation and combinations for this equation. So let's say a could be 0, b could be 0, c could be 10, or A or B could be 1 1, or it could be 8. There could be multiple uh, combinations for this. I think in mathematics we use something to determine what could be total possible number of solutions for a given equation. Let's just ask from that chat GPT. Uh, given that a plus b a plus b plus c equals 10, and a comma b comma c all are greater than 0, then what is the total number of solutions as well? Solutions for this equation. Positive, exactly. So okay, so that's the formula. N minus 1 c k minus 1. So that's n minus 1 factorial divided by uh, n minus 1 minus k plus 1 factorial times k minus 1 factorial. So this will cancel out and we'll eventually get n minus 1 factorial divided by n minus k factorial times k minus 1 factorial. Okay, where n equals 10 and k equals 3. Okay, n equals 10, k equals 3. So therefore the total number of solutions, so there for this particular problem we could have 36 number of permutation and combinations for a, b, and c. Okay, so that's what we are doing over here. Okay, let's just get back to the lecture.
1 or 2 tickets, right? So
I think I'm unnecessary, stretching the lecture, because I think the recording is now this 1 hour 13 minute lecture has been extended to over 3 hours of lecture, I guess, more than 3 hours.
Alyssa
But anyways, because that's the time where we are actually learning the core idea behind the Python.
can sell 0, Ben can sell 0, Cindy can sell 0, Alyssa can sell 0, Ben can sell 1, Cindy can sell 0, and so on. So we're basically having these 3 for loops that make all the possible combinations of tickets. So here I have Alyssa, Ben, and Cindy trying to sell tickets to a fundraiser. And then I have my system of equations here. So in total, they sell 10 tickets. So here, total
Okay,
two.
so like here's what's happening for Alyssa in range. So it starts from the 0. For Ben, it again starts from the 0. For Sydney in range, it again starts from the 0. So C, A, B, C initially have value for 0. Total equals A plus B plus that equals 10. Is that a Boolean value? Is that a Boolean value? Exactly. So this particular is a Boolean value. So 2 less. So over here we have a variable which is equals, then equals less or minus 2. Oh my God. So we are again creating a Boolean value. Okay. Okay. I'll tell you what. So here's what we are actually doing, you know. So mathematically, what we do is we plug in the values, you know. So by using maths, basically what we do is we plug in the values. Let me just get that right. Plug in the values. But in Python, what we are doing is we are imposing Boolean Boolean values, and then we are checking if the given statements, which was these three statements, b equals, you know, b equals a minus 2, c equals what I guess it was 2a, Alyssa, 2 times of Alyssa, and then there was the third equation. What was the third equation? Uh, okay, so this was the third equation. Uh, the third equation was a plus b plus c equals 10. So by giving them Boolean values and changing their values alternatively, we are verifying if these three conditions satisfy at the same time. So checking checking if they are getting satisfy getting true, true at the same time. And you might ask that what is that time? So the moment a get equals 3, you know, and the b get equals 1, and c get equals, I guess it was 3, maybe, no, it was 6. The moment these three value comes, this is the basically the time where these three particular statement gets true. In that case, we get the value for our variables. So this is what brute force, according to what Gemini said, you know, is yeah. So brute force search, or the exhaustive enumeration, I really don't know what that means. Let's search for this word. Enumeration meaning. So a problem solving algorithm that involves systematically listing, testing, and defining every single possible options. Okay, so in simple language, it basically means checking every permutation and combination. So we just talked about this. We just talk about this permutation and combination, that there could be 36 permutation and combination. Out of these 36 permutation combination, one of the combination is basically this. For this particular combination, our these three conditions get satisfied, and hence we get the true value, you know. That's really fantastic. You know, we could use Python in such a way. That's, I mean, this could probably be used in hacking or something. That's amazing.
Less than twice are all Boolean variables. So a plus b plus c is equivalent to 10 is the first condition I need to hold. B is equal to a minus 2 is the second condition I need to hold, and c is equivalent to 2 times a is the last condition I need to hold. Those are the
Wait, what time it is? Oh, it's 10 p.m.
conditions from the previous slides, right? And so these three Booleans, whenever they hold, total is true and 2 less is
You know, so here we are satisfied. We're checking whether these three conditions are true at the same time or not.
true and
So if three of them are true, it's going to print the following, or the respective values of A, B, and C.
twice is true. When all these three things hold, I have found the solution to my problem. So inside my code, this is Alyssa, Ben, and Cindy trying to sell
So this code is very slow for large numbers. Okay.
tickets, and the code automatically tells me they sold this many each. And what's cool about this code is we can then change something about it, and then we can run it again, and immediately it tells us what the new solution is. We don't have to do it algebraically and solve it all over again. The problem with this code, and the way I wrote it specifically, is it's really slow for big numbers. If I change it to 1,000 tickets being sold by 3 people, right, and then a couple other changes here, just the sheer fact that I've got Alyssa iterating through 0 to 1,000, and Ben iterating through 0 to 1,000, and Cindy iterating through 0 to 1,000, it takes really long time. And so that particular code, I'm not even going to run it, will take a really long time if I change the values to be 1,000, 20, and twice. But instead, we can use kind of a mix of algebra and computation to solve the problem. We recognize we actually only need a loop through one loop, right? I only care about maybe checking Alyssa's number of tickets, being 0 through potentially 1,000 tickets sold. And then I can use my other 2 equations, right? Ben and Cindy, how many did they sell with respect to Alyssa? And then I've got my 2 other equations here, which will tell me how many Ben and Cindy sold with respect to Alyssa's loop, right? And then my last equation here is that Ben and Cindy.
So what they're doing over here is for Alyssa in the range till 1,000, Ben equals max. What is this max function? What is max function in Python? What is function Python? The Python usually outside of it variable. Okay. So it's basically similar to finding the maxima of a given given item, like a list or a tuple. Okay. Okay. All right.
And Alyssa altogether had to sell 1,000. And so with this particular code, I'm able to find the answer to the question, which is how many tickets they sold. And again, this is.
So maximum of Alyssa minus 20. Okay. Sydney equals Alyssa times 2 if Ben print. Okay. I'm not able to get this code 100%, but I'm gonna keep my focus on it. I'll try to understand this later. Okay. I'm just getting the basic idea, but I'm not just deep diving into this code. This must be interesting, I can already say, but I have to complete this lecture, so I'm just going to rush a little bit.
Really awesome because now
We're just left with 10 minutes, maybe. Yeah, 9 minutes, 22 seconds.
I can make small changes to the numbers and solve the problem basically immediately like that, right? I don't need to go back and solve it algebraically as I would if I were to do math. Okay. So we can apply computation to many different problems. I hope that this is a really good showcase, this word problem of what we mean by computational thinking and the kinds of things we want you to come away with in this class. The last thing I wanted to talk about, and I'll just do a quick intuition, is binary numbers. And this is actually a precursor to the next algorithm we're going to see in the next lecture, an approximation algorithm. It's going to be an improvement on the guess and check algorithm. So
okay.
And solve the problem basically immediately like that, right? I don't need to go back and solve it algebraically as I would if I were to do math. Okay. So we can apply computation to many different problems. I hope that this is a really good showcase, this word problem of what we mean by computational thinking and the kinds of things we want you to come away with in this class. The last thing I wanted to talk about, and I'll just do a quick intuition, is binary numbers. And this is actually a precursor to the next algorithm we're going to see in the next lecture, an approximation algorithm. It's going to be an improvement on the guess and check algorithm. So far we've seen numbers in Python. They can be integers, which are whole numbers, and floats, which are real numbers.
Our motivation keeps us in a mind for the next few slides that All right. Print x equals, okay. 1. So that's true. This should be true. Print x times 1. Okay.
But in programming, some interesting things happen when we deal with floats.
Okay.
And this is going to be our motivation for talking about binary numbers and then fractions and then floats in this lecture and then in the next one. So here's an example.
Wait, what's the next lecture that we'll study? Let me see. So it's floats and approximation methods. All right. Oh, there we go. Decomposition, abstraction, and functions. That's what we were talking about over here. Um, Computational. So, okay.
Of some code. So I've got, is exactly what's in the slides. I've got an integer x, and all I'm doing in this code is I have a loop through range 10. So that means it's going to loop through 10 times.
Let me see if, yeah, perfect.
And I'm adding 0.1 10 times. So 0.1 plus 0.1 plus 0.1 10 times. And I'm going to print whether x, this sum, 0.1 plus 0.1 plus 0.1, is equal to 1. And just to show you I'm not pulling your leg.
So that's, no, wait. Here's one thing. The output for this particular thing should be false because 1 is basically an integer. 1.0 is basically a float. And in our case, x is basically a float number. So a float is not equals to an integer. So my intuition tells that it's going to be false.
I'm going to run it
False.
and print
false.
Whether x, so 0.1 plus 0.1 plus 0.1 10 times is
But if you write 1.0, it's going to be true.
Equivalent to 1. And this code prints false. Not intuitive, right? If I'm adding 0.1 10 times, I should be getting 1.
Yeah.
But I'm not in programming. And just to show you the actual answer we get, let's print what the value of x is, and then ask whether that's the same as just multiplying 0.1 by 10. So doing the loop where we add this number 10 times.
Wait, what? Wait, what the hell? What's that? 0.99999? Wait, why that's happening?
Gives me actually 0.9999999. Whereas just multiplying 0.1 by 10 gives me 1, as I expect.
Wait, so it's not just the data type, but it's actually the value of the x itself, which is not same as 1. Holy shit.
Okay. And this is the motivation for, or I guess the precursor to our next algorithm, the approximation algorithm. Okay? So we have this thing called a floating point error. And why does it happen? And since it happens, we can't do equivalency, right? We can't use the equal sign between floats because we get things like this that are
So we can't use equal equals operator, for floats.
going to completely mess up our program when we expect, something as simple as adding 0.1 to itself 10 times to be 1, and it's not, right? And so the big idea here is we have operations on floats, and because of the way floats are actually stored in computer memory, these operations introduce a very small error, super, super small, every time you do an operation with a float. But the more you do this operation that has
So there, because these operations, OPREA operations, lead to small errors, which adds up to a significant error, which adds up to error if repeated or if done many times.
This tiny error,
So that's a really good explanation.
the more this error gets magnified, right? And so then we see surprising results like that. And so that comes about with the way that floats are actually stored in the computer. So what we have in the computer is we work with binary, zeros and ones. But humans actually work in base 10, right? We think from 0 to 9. But the computer works in base 2, either 0 or 1. And the reason it works through 0 and 1 is because of the way that the computer hardware is built, right?
Exactly.
It's easy.
So a lower voltage or a higher voltage, that's what it means. It's if it's ground, or if the voltage is 0, then it's 0. If it's non-zero, then it's 1. Exactly, that's what they just said. Voltage is a high or low, or magnetic spin is a up and down. So I think the magnetic spin is basically that term is used for an electron, an up magnetic spin electron, and a down. Okay. Fine for the integer arithmetic, but what about the numbers with the fraction parts?
For the computer hardware to say that a magnetic spin is up or down, right? 0 or 1. It's easy for the hardware to say that it has a voltage that's low or high,
Okay.
right? If it would be a lot harder for the computer hardware to say, hey, I have a voltage that's 0 low, high, let's say 1, or it's 1/10 of the high or 2/10 of the high. There would be too many errors introduced. And so it's a lot easier for the computer hardware to just be in one of these two states, 0 or 1, right? So that's where binary comes in. And so when we're dealing with integers, this is not a problem because we can easily.
So base 10 representation of an integer, sum of powers of 10, scaled by the integer from 0 to 9, exactly. Okay. Binary representation is same as the idea in base 2. Sum of powers of 2 scaled from, okay. Okay, all right.
Convert.
So 1 times 2 raised to power 10 plus 1 times 2 raised to power 8, 7, 6, 5. Okay, 1, 0, 1, 5. I don't understand this particular pattern. Okay, whatever. 0, 1, 5, 6, 7, 8, then 10. Okay.
Numbers that are in base 10 to base 2, that are whole numbers, integers. The problem will come when we do floats. So you don't need to know how to do the conversion, but it will give you an intuition for what's going to happen. So the number 1,507 in base 10, so that's what we have up here, is 1,000 plus 500 plus 0 times 10 plus 7, right? In base 2, we have a similar pattern. We have some whole number multiplied by some power of 2. Here, we had the whole number be either numbers 0 through 9 multiplied by some power of 10. But in base 2, we're going to have either 0 or 1 multiplied by some power of 2. And if we're trying to convert the number 1,507 from base 10 to base 2, I guess humanly speaking, the way we'd think about it is, what is the biggest power of 2 that we can have that takes us close to but not over 1,507? And that's 2 to the 10, 1,024.
All right.
Because 2 to the 11 is 2,000 something, and that's already too big. And then you ask yourself, what's the next biggest power of 2 I can add to this number, 1,024?
So it's basically, so if human has to find that, if a human has to convert 1,507 to the base 10 to the this number to the base 2 for the computer to understand, we could just use hit and trial method, you know.
brings me close to but not over 1,507. That's going to be 256. Notice we skipped 2 to the 9 because adding 2 to the 9 takes us over 1,507. It's adding 512 to 1024. And so we repeat this process where we're basically trying to figure out what are the biggest powers of 2 we can add in order that makes up 1,507. And it turns out it's going to be 2 to the 10 plus 2 to the 8 plus 2 to the 7 plus 2 to the 6 plus 2 to the 5. 2 to the 4, 3, and 2 are all going to be zeros, and 2 to the 1 and 2 to the 0. And the bits, right, 1 times 2 to the 10, 1 times 2 to the 8, is basically what gets represented here, right? These whole number portions that we multiply the powers of 10 by. And that's how we convert from a decimal number to a binary number. But again, this is kind of a human way of converting. We can actually do it in a more systematic way, a more imperative way, right? A recipe way, some way that a computer can actually use to take a number and convert it to binary. And you would never have to come up with this way, but given this way of converting to binary, you should be able to code it up.
So consider x equals 19 to the base 10. That's basically this number over here. If we take remainder x raised 2, that gives us the last binary bit. If we then integer divide x by 2, shift it right. So, okay, keep doing successive division. Now the remainder gets next bit and so on. Let's convert to binary form.
So the idea here is we're going to take a number and we're going to look at the
Okay, I need to understand this. This. Using the two basic math operators, you already know the modulus and the flow division function. So what did the flow division function did? I have actually forgotten that what did the flow division function did. Let me just revise my notes. Let me just look into my notes so I could find out what did y division to avoid the extra work. Float. They go by such a way that it gives the float always coming. Okay, so it's like rounding off. So the flow division, what it does is basically, so let's say 3 divided by 2 is basically 1.5. That's a float. But 3 divided by 2, or basically using a floor integer operator, it basically gives 1. I hope so. Yeah, yeah, it does. So when you look at the binary number for 19, it's okay. The slide loops red circle around the last bit to the right one. In binary, the last bit tells you if the numbers are odd and even. Okay. Odd, it must end in if it's even. So 19 is an odd number, and okay, all right. How to check if a number is odd and remainder exactly. Step-by-step mechanism. Oh, I'm like genuinely tired right now. It's 10:22 and I'm genuinely tired right now. Let's just complete this lecture.
the remainder when we divide it by 2, right? If it's an odd number, obviously the remainder is 1. If it's an even number, the remainder is 0. And that remainder actually gives us the last bit, the farthest right bit.
Okay, so here's what we are doing. Initially, the step 1, we are using the modulus function to determine whether the number itself is an odd number or an even number. So if it's 1, if we get remainder to be 1, then it's an odd number. If it's 0, yeah, it's 0, then it's a even number if I'm not wrong. Let me see. So for odd it should be 1, for even it should be 0.
And then we can take that number and divide it by 2 fully. And then that
Shifted to right. So what do you mean by shifted to right?
gives us the remaining 4 digits. So you see everything else just gets shifted over. And the way the code looks is just doing something else, just gets shifted over. And the way the code looks is just doing successive divisions and figuring out the remainders. So I'm just going to look at the Python tutor real quick, and then we can stop. So if we're trying to convert the number 1,507 following this particular recipe, all we do is we look at the remainder when we divide the number by 2. So this is an odd number. Obviously, the remainder is going to be 1. So we add a 1 to our binary representation. And then we're going to keep adding what happens when we divide the remaining numbers by 2. We're going to keep adding the remainder to the front of this string here. So if we divide the number 1,507 by 2, that gives us 753. And now we ask, is 753 odd or even? It's odd, so we add another 1 to the front of this string, the result string. Divide 753 by 2, it's 376. This is even. So now we add a 0 to the front of my string, right? Okay. So notice what happens to this.
All right. So that's what they're doing. So basically you're given a number, so let's say 20, and what they're doing is dividing it by 2, and if the remainder is 0, they add 0, then it gets 10, it again gets 0. So let me write this over here. 0 divided by 2 is 5. Then you again divide it by 2. Now the remainder is 1. Okay, so it's now 2.5. You again divide it by 2. I guess that's 1.2. No, for 0.5. For 2, it should be 1 plus. For 5, I guess it should be 0.5, 0.25. So you get, not approximate, but you get 1.25, which is an odd number. So you get 1. Then you again divide this by 2. So you get what? 5.5 plus, what's the half of this? That should be 0.125. 0.125, I guess so. Let me just use calculator. So 0.25 divided by 2 is 125 exactly. So that's what, 0.625. That's again what, odd number. Then 0.1625 divided by 2, that's 3.125. Wait, am I not supposed to stop over here?
String as we go step by step. 376 divided by 2 is 188. What is this?
That's an even number, so we are going to add 1 in the front.
Even number?
No, it's even, so we are going to add 0 in the front.
So we add a 0 to the front of this string.
Exactly.
188 divided by 2 is 94.
0.
Again, it's an even number, so we add a 0 to the front of this string. 94 divided by 2 is 47, it's odd, so we add a 1. 47 divided by 2 is 23, it's odd, so we add a 1. 23 divided by 2 is 11.
All right. So basically we are taking the floor integer. Oh my god. Okay. I get the idea. So let's say let's do this over once again. So 20 by 2 is 10. So we write 0 because it's an even. 10 by 2 is basically 5. So what's 5? That's an odd number. So we write 1. So 5 divided by 2 using, this is basically 2. That's an even number, so we write 0. Yeah, And 2 divided by 2 is basically 1. That's an odd number, so we write 1. So 1 0 1 0. Wait, uh, 1 0 1 0, and a binary to number. That's 10. I think I got binary to number. So number to binary converter. Let's say it's 20. Okay, I must be doing some mistake over here.
So we add an
I'll check that out later.
odd. So we add a 1. 11.
So yeah, 5.5. So it's 5. It's odd, so we're gonna add 1.
11 divided by 2 is 5, so it's odd, so we add a 1. And then 5 divided by 2 is even, we add a 0, and then 1 is our last number, so we add a 1. And notice, this is the exact same number we had when we did it in this human, thoughtful way,
Okay.
where we were trying to figure out the highest powers of.
So that's a very efficient way to find a very efficient algorithm to find, to convert any number into a binary.
2 we can take to go up to, but not
Oh, that's crazy.
over the number 1,507.
Let me just take a screenshot of this.
Can take to go up to, but not over the number 1,507. Okay, but we did this using just this very iterative, very nice loopy code. And if we wanted to do a negative number, we would just add these 2 boxes here. It just basically means we add a negative sign in front of it. Okay. Yeah.
So really good. Go to convert a number into a what? Into a binary number. In fact, I can do that on my pen paper. Just explain the steps. Okay. Oh my god, 4 hour of recording. That's hilarious, man. That's freaking hilarious. Okay. Let's just race through this code line by line in your paper. This logic is identical how you calculate it by hand. But the string concatenation on the lines is a brilliant trick to make sure. Okay, so running the loop. No. Wait. No. Wait. Explain the basic idea. Don't explain the code. Explain the algo. Chop and check game. Think of it peeling layers of the number right from the left until there's nothing left. The setup, you start with your base number, like let's say 30, and an empty piece of paper you would write down. Code loop, even grab. Check for or grab the remainder. Look at the correct number. Is it odd or even? If it is odd, write 1. Okay, let's do it. Let's do it for 13. Let's do it for 13. So our x is 13. So it's an odd number. It's an odd number, so we are gonna write 1. If we divide it by 2, what we get? We get 6.5. 6. So we get 6, which is an even number, so 0. So 6 by 2 is 3. 6 by 2. Wait. So 6 is an even number, so we wrote 0. 6 by 2 is 3, so we wrote 1 because it's an odd number. 3 by 2 is 1. 1. What is 1? 1 is an odd number. Yeah. So 110. Please tell me it's 110. So it's 110. Please tell me. Okay. So I totally understood the algorithm to find, and I think that's all for today's lecture. we did recording for almost 4 hours, and you can see my eyes. I'm feeling really, really sleepy right now. But anyways, all right, goodbye. I'll see you tomorrow.